And we are live. Hello, hello, speaking to you through the internets. We should be live on YouTube, LinkedIn, and now Twitch, if I've configured it correctly. Hey, George, how's it going?
I'm good. It's going over here.
The 8-hour time difference between me and George makes scheduling these things sometimes a little difficult. Either it's super late for me or it's super early for him. However, we have had a few late ones, so time for you to have an early one. If that makes sense. So we're going to have a bit of a pre-show. It's been a busy week, and I don't just mean new administration or YouTube drama or well, the main topic of today's show is going to be Nvidia 5000, RTX 5000. Funnily enough, short story time. I had to take this out. My 4090, I had to take it out of my main PC because it's been giving me a bit of jip. As in, it's just... you remember back in the day when SSDs didn't have trim and sometimes they would pause for half a second?
Yes.
Imagine the system doing that between 30 seconds and 2 hours, but every time it would reset your video driver as well.
Huh. Interesting.
I don't know what it is. I took it out. I managed to carefully remove the easy latch from the PCI slot as well.
Yep.
As you do. Put in my 2080 Ti. Buttery smooth. Perfectly fine.
Interesting.
So I don't know whether it's the weight of this on the slot is causing some bad contact, but it's screwed in fine and it looks supported fine.
It could just be. I mean, my XTX.
I've got latest drivers, latest BIOS.
I mean, yeah. After about 2 years, my XTX just decided to. Well, it just died for whatever reason. So
it's I don't know. So I mean, one benefit of having a 2-slot Founders Edition 5090 is that it puts less strain on your PCI slot, I guess.
True.
But part of the annoying thing is because it's a Threadripper system as well, and I'm looking at it. It's saying 81 degrees CPU, fantastic. Is that you have to have AMD drivers installed for the chipset, and you have to have Nvidia drivers installed for the graphics card, and sometimes they don't play nice. But no, 2080 Ti is fine. I just no longer have access to Easy AV1. But we'll see. We'll see. The thing is, I don't. It's Dom says printing a GPU support stand. I don't think it's the fact that it's heavy, because it should. I don't know. Though, funny enough, cases are the devil.
Yes.
Because once you get a good case, you want to keep it. However, you realize that every case that exists, not one will be 100% what you want. It's either, if you get one that does everything, it's too big. If you get one that fits what you need today, it won't fit what you need tomorrow. Doesn't have enough PCIe space or storage, or but then over time you're thinking, oh, it's 10 years old, I'll get a new one. But then you actually no, this is pretty much feels brand new, unless it's actually been dented or warped and stuff. Why did it last so long? But no, the one I've been looking at, it has the motherboard horizontally, because I think we spoke about this last show.
Yes, yeah, the new Silverstone case. I think it's Silverstone.
No, the Johnsbow N5.
Oh, the Johnsbow. Yeah, okay.
Which is it's meant to be a NAS case, and
yeah.
See if I can share this. Share screen. Are you going to be nice?
Technology being nice? No, never.
Johnsbow. Okay, here we go. It's this one.
Yeah.
And the idea inside is you can fit 12 hard drives, but also put in a full XL-ATX system at the top. And like, great. One, my setup doesn't allow that sort of size device, and two, the other reports is that it can be slightly loud. I mean, you could put quiet fans in it, I guess. And
well, I wonder if that's slightly loud with all the hard drives installed, because that's a different kettle of fish.
Yeah, I don't know. It's but then I have another case. I still have cases from builds ago, and you can't see it, but when Intel sampled the overclocked 28 core 3175X, they sent a whole system for that. I've got a Xeon Phi system over here. I've got a couple of spare systems from my benchmarking days here. At some point, you end up with too many cases. I know, it just sounds like I'm boasting now, showing off my 4090 and talking about new cases.
Yeah, just showing off all the hardware you've ever had.
You know, I need to get rid of so much of it.
I mean, you know my address.
Yeah, I can't ship all of it across the seas though. It comes back to what we were talking about last week with Strix Halo, right? If you get that in a right size build or the right amount of storage, I think that can be quite nice.
If anyone from HP is listening, send me the Z2 Mini.
It's G2A, or is it or something?
It's the HP Z2 Mini G1A.
Okay, that makes perfect sense. Of course, that naming does.
Well, okay, so it's HP, and it's the lineup it's the Z2 lineup. It's the mini system, and it's the generation 1 of the AMD version. So it actually does have a semblance of meaning.
Yeah. Okay. But then on top of that, stick in something like an RTX 4000A Ada or something. Single slot, high performance, rendering engine. And I'd say that just simply because not a lot of rendering programs are optimized for AMD right now. Or there are certain features that you can get with the NVIDIA driver set that you can't get with an AMD set. Things like my teleprompter, that is right there, that requires an NVIDIA GPU to use, because it uses some of the NVIDIA AI features as part of broadcast to do what it does. So, and speaking of NVIDIA, maybe we should start the show as people are flying in. Hello to everyone. Davina, well, Jeff from Craft Computing was in first. I'm not sure if he stayed around yet though. And then Davina, Huey, Hackneo, Lewis Friend. It's going to be a fun show, and let's get. I'll change the banner now. Let's change the banner.
No more the pre-show.
These banners are sometimes annoying to arrange, but anyway. The Tech Poutine. So welcome one and all to the Tech Poutine. This is episode 15. Your once a week source of some things we enjoy about technology. I refuse to call this news now. We just talk about stuff we enjoy, right? It's something maybe related to stuff that's happened this week. And well, this episode is actually a good example of that. My name's Ian. I run More Than More in Tech Potato, and joining me, as always.
And I'm George, and I run Chips and Cheese.
And it's Tech Poutine. If we had a guest, there'd be gravy, but we don't. And we should probably start doing that soon. Otherwise, people.
I was going to say, maybe we should get Jeff on one of these days as a gravy. Have beer gravy.
Yeah, well, he's also got a 5090, so he's got +1 to both of us.
True.
It's and thanks to Jeff for providing some of the stuff we're going to speak about today. However, topic number 1 is going to be NVIDIA has officially lifted the embargo for RTX 5000 or 1590 series reviews. Has anybody reviewed any of the other cards? Did anybody?
It's just 5090 for now. I think the embargo for the 5080 is rumored to be the 29th. I'm not sure if it is the 29th or not.
I'm not under embargo.
It's just the 5090.
neither I nor George are under embargo. Neither of us. It may see why are we watching a video of people who didn't get the card? Because we're going to analyze some of the architecture and some of the features. Yeah, if anybody from Nvidia is watching and you're thinking, hey, aren't we sampling these guys? No, you're not. I asked very strongly for access to Editor's Day at CES in order to get pre-brief access on the benchmarking and the features, and was denied several times, even after reaching out 2 weeks early. But there we are. That's my relationship with NVIDIA right now. If you happen to be at NVIDIA and want to change that, please let me know. But RTX 5000, we have now this $2,000 MSRP GPU, which is likely to be scalped. I saw a report saying here in the UK, one of our retailers is only going to have single digits at launch, much like before. However, it is finally, I mean, I pulled up a tweet I made back in late January, early February last year, joking about what the size of the 5090 would be. Because realistically, the launch of the 5000 series is later than normal cadence, and that's because they can, because they have a lead, a peak performance lead at any rate. You know, performance per watt or performance per dollar is something slightly different. But 5090 now 575 watts in a dual slot form factor. I'm glad they're going back to dual slot with the card. 575 watts in a dual slot. So the thing is, there was actually I'm actually going to bring up a tweet here, if you bear with me for a second, because it's something I responded to, and
well, I know that the so sort of starting to get into it. The FE can, because of the pass-through nature of it, depending on your case, can cause some CPU throttling, just because of the sheer amount of heat that it's putting out, and it will.
So it's got a blow-through cooler. So the cooler, so the fans will literally blow through the card. Yes. Normally, most cards, it will blow up and then out or out. So instead, the Founders Edition ones just blow all the way through. But
which is more efficient in terms of cooling.
And it will do it on both sides as well. So there's the GPU in the middle, for example. It's not the middle, but you know what I mean. You'll have a fan on the left, a fan on the right, and they both blow all the way through.
Yep. But in the 5090's case, it is directly in the middle to allow for that airflow.
Yeah, it's but as you say, the fact that you're pumping hot air now into the area of the CPU is causing CPU temperatures to rise. But at best, I've seen what, 4 degrees, 5 degrees, worst case.
I've seen I forgot who was doing the testing, but I did see like a 10 to 15 degree delta. I
guess it depends whether it's open case or closed case.
Also, I wonder what that's going to do to people. So I know a lot of people like to run XMP or Expo. I wonder what that's going to affect memory overclocking.
You will end up, because due to the thermal variation, there will be some instability. That may be actually caused by the temperature delta changing, rather than if it was a constant applied heat, something you get a fixed differential, but because it's a variable temperature heat. But yeah, I want to bring up this tweet here. Why is the RTX 5090 575 watts? You can run it at 500 watts with 100 megahertz OC in the same performance. And the thing here is that we're talking about silicon lottery, right? For those of you who don't know what this is, when you build a chip in a fab, you have to test to see what the frequency and voltage response is for a given power. And you end up with a graph of, you know, what voltages work at what frequencies. And you'll find that different chips have different optimal points. The way I sometimes liken this to is a batch of chocolate chip cookies. Some cookies have more chocolate chips. So when you make silicon, due to stochastic and randomness and physics, some chips will naturally be better. Now, the ones with defects invariably do worse. You might have to cut something off. You may have to bin it as a lower part. But this binning process also occurs power. And because you've got the top end skew, your top end variance can be massive. If you've got a super really efficient chip that's badged as in this case, a 5090, yeah, it can run 100, 150 watts below the rated power at a higher frequency, and you get more performance out of it. Good for you. You've got a great chip. Hold on to it. That's what we mean by silicon lottery. This is why overclockers go mad over what we call cherry bin CPUs and GPUs, because if you can find the chip that does 6 gigahertz at 0.7 volts, then maybe it'll do 9 gigahertz at 1.6 volts, that sort of thing. So
yeah,
but because of this variation, right, Nvidia already does some of that binning with their Max Q and their Max P laptop chips. But if you've got, say you want to put this in a small form factor, right? Maybe you want the top 10% performing GPUs to go in. You then have to do that testing. So why is it 575 watts? It has to be a catch-all for every chip that goes into the market. It's it's the same with CPUs and frequencies. So when Intel says this chip is a 3.2 gigahertz at 65 watts, what that means is at 65 watts you'll get a minimum of 3.2 gigahertz, or at 3.2 gigahertz it'll hit a maximum of 65 watts. If it goes beyond that, technically you're out of spec, and you could theoretically warranty it. GPU is a bit different though because of boost.
Jeff in the chat says, I saw a number of closed case reviews with only 3 to 4 C rises in CPU temperatures. Those with AIOs and less airflow over the motherboards could raise memory and VRM temps. Yeah.
Davina says, imagine undervolting a 5090. So funnily enough, most Zen 5 CPUs that are rated at like 170 watts, if you run them at 75 watts, they still have about 90% of the performance.
Yeah.
And you save power.
It's because you're hitting that end of the bell curve to squeeze out that 3 to 4 more percent.
V equals IR.
Yep.
What's the I squared C one or whatever? Yeah.
Isn't that?
Come on, physics boy.
I should know this off the top of my head. I don't.
I should. I'm bad. Oh, sorry, wrong one. Say remove George. Okay, so let's go to talk into some of the slides. Actually, let's start with the Blackwell architecture, so we can go through this with you all. Actually, do we want to speak about the technical, or do we want to speak about the reviews, just to bring everybody up to speed? Actually, yeah, let's start on reviews. Executive decision reviews.
So,
we'll come to architecture in a bit. You have to stay for architecture.
Ohm's law. It's I squared R.
Yeah. So reviews brought, I've seen a few reviews. George has seen a few reviews. We've got reviewers in the chat. By and large, for your 25% increase, you get a 25 to, on average, 30% performance increase, and a 25 to 30% increase in power. That, if you want to do something special like 4-bit AI, you get a massive improvement. So people are saying, if I'm getting, for that increase in price, for that increase in power, and I'm getting the same increase in performance, there's no efficiency improvement, right? Performance per watt and performance per dollar is the same, and historically, NVIDIA have always improved those benchmarks. If you then start to go into using some of the specialized features like DLSS4 and frame gen, on certain titles, you can get more than that speed up, but by and large, for the titles that don't, you're going to get what looks like a like-for-like improvement. Now, this chip, compared to previous gen, you've gone from GDDR6X to 7. It's a higher performing memory. However, you have also increased the size of your compute. So
I have to, off the top of my head, the compute increase actually is less than the memory bandwidth increase. The compute increase is about 40% for FP32 and 16, if I remember correctly, whereas the memory bandwidth increase is 80%.
It's Kiwis always says if you work in AI and ML, the extra VRAM and memory bandwidth alone are probably worth it. Yep, 32 gigs of GDDR7. Yeah, nice. About time. And Wobbo says performance per dollar is improved for RT heavy workloads like Blender. Yeah, if you're using the special NVIDIA only features optimized for NVIDIA hardware, as always, these are pretty good. And was it 4th generation RT cores? We'll get into the architecture.
Yes.
So we can do inline 32 sets of matrix operations. Again, we'll get into that with the pictures. But yeah, the thing I think is being lost a little bit is that NVIDIA has still pushed the peak performance out 25, 30%. That's not easy, right?
No.
So you're always going to pay more for peak, and you're always going to be outside the efficiency window for peak. The card that goes 235 versus the card that goes 238 versus the card that goes 241, right? You're going to be paying almost double for that last car than you are for the first, just for 6 miles an hour, because that's the way some of these things work. People are a bit confused about the efficiency being roughly similar, because we are now using a Blackwell-based new architecture N4 chip. The thing is, a lot of the architecture, as we'll see, has gone to new features rather than just raw compute. But also, you're still sticking the power up, and you're still going outside the efficiency window to get that boost. So the thing is, I think I saw a lot of people, mostly in the comments, not reviewers, imagining that price to performance and performance per watt is this straight line based in the origin. And you've always got to go above and beyond what the other one did. You can't just keep traveling along a straight line. And I'd argue, no, if you're hitting the peak, this is just 5090. When we get to 70 and 80, it's obviously a different story. But just on 5090, the fact that you've pushed it beyond that's the value add you get with that product. And yeah, they'll sell out. So
always.
But yeah, no, I found a lot of the reviews to be relatively fair. I did see somebody, was it Andreas at Hardware Lux, posted a photo showing his 12-volt high power pin cable at almost 60 degrees Celsius. That's not great.
But that's if I remember correctly, that spec for the connector is like 85C, so that's well within your spec.
To be honest, this is actually the first time I've seen people look at temperatures at a GPU review, and okay, they might have gone up slightly from like 79 to 83, or it's making my CPU go up 4 degrees, and the response has been, that's all right. In previous years, it would be daggers at dawn. You increase the temperature of my chip. How dare you? I also did see somebody else talk about the thermal hotspots of the memory, because it's GDDR7 running at such high frequency, might be a bit of a concern. So I did tweet. Was it DeBauer who did that?
DeBauer, and I think Tech Power Up too. Both.
I think the next set of benchmarks I want to see is performance with memory downclocking.
Yeah, I mean, put it all on a level playing, like for 4090 versus 5090, same memory.
Yeah,
speed at least.
Oh no,
you would have to underclock Or are you talking about like performance
Yeah,
versus like just 5090
performance.
performance? Okay.
Yeah,
Okay. I thought you meant like trying to get equals to equals comparison. Like that would be kind of difficult.
No, no. If I can declock the memory 20% and get it 20 degrees cooler, and there's no real effect on performance, except in ML workloads and maybe some RT workloads or whatever, that's fine. Then that's what I'd do. Yeah, and also I did see your comment a few times. Don't worry.
See, my gut says you reduce memory bandwidth. That's bad because GPUs are usually memory bandwidth bound. But in this case, I don't know. Like at least in games, right? Productivity, ML, of course, they'll be affected. But
I'm just thinking, what game do I play which actually stresses my 2080 Ti, let alone my 4090?
Yeah.
Right now, my game of choice is browser-based, and it's called Farm RPG. So I can run that on a potato.
Yeah, no, the games I play are like Europa Universalis 4, Stellaris, Hearts of Iron 4.
No, I fired up Diablo 4 and Saints Row, the new one, recently. So actually, one thing I want to highlight what Darkman said. Why can't we just have good silicone sheathed 2 lead cables with nice chunky connector made for the task, as opposed to the crap of 12 awful cheap PVC coated wires and an old connector? Cost.
Yeah,
right?
Cost.
Yes, if you're at a position where you think if I add $10 to the cost of this connector, it would be amazing. Now you've got to do it for the 10 million GPUs you're going to sell.
Yeah.
You could
the economics of scale don't work out that in that favor.
Well, this thing, you could argue for the 4090. Yeah, adding $10 to a $2,000 chip. Oh, sorry, 5090. Adding $10 to a $2,000. This, if you were to design a no compromise solution, well, it would be 8 slots for a start. That's just yeah. You'd have 20.
With what power supply are you gonna? Like you would have to have a bespoke connector on the
silicon carbide and gallium nitride power supply. Yes,
I guess.
So there is that.
Yeah.
Yeah. Okay. Let's go into architecture. So I've briefly gone over these slides. I think we just sent George them, so we're going to get live reaction from George. So please butt in.
I've seen these on various websites, but yeah.
So let's disagree with slide 2. Moore's law isn't dead. We're in the we need more than Moore's law. Wait, there's a company with that name. So,
pay for the trademark.
Yeah, what, like some other people? Yeah, but Jensen, what he really means to say is you don't get anything for free now. There is still Moore's law. You still get density and you still get packaging. You just also have to get performance in other ways, especially with such an optimized workload like graphics.
Yep.
I will point out, Elad says DeBauer talks about not having a hotspot temp, which was a feature in the 4000 series, which is a hardware info number that just tells you the hotspot on the chip based on the thermal sensors. That's not here this year, or this generation. So how do we get more performance? We use neural rendering, which is, I hate the intercalation of biological brain terminology with machine learning, because it's so abstract. Especially, we don't render with our brain. What? No, we don't raster with our brain.
No, we ray trace with our brain. Oh wait, no, that's your eyes, bottom Tish.
Yeah.
I mean, don't you want an RTX face?
Our brain is a display output, and our eyes are a buffer.
So you mean input?
No, because you act on what your brain brain gives you, but you are your brain. So, okay, we're getting a bit metaphysical.
Also your
now.
brain takes in the input, so it's all the above.
Well, no, your eye's taking the input. It's processed by the time you get to the brain.
It still has to be sent over. Like, it still has to be sent over the bus called your neurons.
Topic exhausted. The point is, if you add machine learning, you don't need to raster all the pixels, and that's why. So here the metric is AI tops per frame. So if you just take top as a chunk of workload, it's a million digits of pi, whatever. This is just saying how many digits of pi per frame do you need? How many AI tops do you need? And right now it's 15, but it's in 2016 we needed 0. 2020 is 1, and we're saying we need 15x what we had in 2020. Now the thing is, because you don't define this, what's 15x of 0.1?
Well, what's an AI top? What data type?
At least FP4. So we see with this slide, we're seeing it with Nvidia, we're seeing it with AMD. They can't just throw silicon at compute anymore, as in raw number crunching on groups of threads, just simply pushing through ALUs. What AI matrix math does, I guess I'll say it this way: when you do a calculation, you say you're doing addition, you add these two numbers together and you output a result. You add these two numbers together and you output a result. Then you add another number and you output the result. Mm-hmm. Rather than outputting the result, what if you just added a number? You don't worry about making a record of your intermediate result. And this is when we get things like DP4A and chained multiply accumulates in GPUs. And so rather than, because any standard calculation in a CPU or in a GPU, running through a standard arithmetic logic unit temporarily stores the result, and sometimes either in a register or it kicks it out back into cache before you can use it again. Things, if you know where you're going to use it, why keep it in register rather than cache and just do another operation on it without having to decode and issue another operation because it's already plugged in? So AMD said back at CES that they're dedicating more silicon to this type of workload, ray tracing and neural rendering and whatever we're calling it today. But also, I guess point 2 here is, if you know what you're going to do with the number next and it's the same function, and not sending out to memory, you save memory bandwidth. So why not?
Well, you don't just save memory bandwidth, you also save memory capacity, right? Because you don't have to kick that. You don't. You just store it in a temporary register or in shishmem or wherever on the chip, because you know that you're just going to reuse it.
Yeah.
So you don't have to kick it out to memory. You just leave it there.
When I first started programming GPUs back in 2009, memory latency was a bottleneck. So it was a case of, or how many operations did you have to do on a bit of data you loaded from memory in order to hide the bottleneck, right?
Yeah.
And
back then
it was like 60.
I was going to say, correct me if I'm wrong, we didn't really have like atomic operations or the level of.
No, we did.
Were there atomics back then?
When I was programming GPUs, we had atomics. They were incredibly slow because they caused a synchronization across an SM.
Oh, okay. Yeah, because I know that back then, what essentially, at least for terascale, what you would do is you would use what was known as the GDS and pull from the GDS, because you didn't really have atomics, at least in the early terascale.
Now we're talking mid 2000s. Yeah.
Yeah, I don't quite remember when Nvidia got atomics, but I know that was not a thing for a while. 20 years of GPU in 5 seconds. But it's but back then you had to do like 60 flops per memory read
in order to cover up that latency. And if your algorithm didn't do that, you sat around inefficient. So it's a way to get around those limitations as well. And then energy efficiency, process node and packaging and such. So yeah, highlights. 5th gen Tensor cores, 4000 AI tops, and high-speed FP4, better than low-speed FP4, I guess. So I'm going to be super sarcastic and devil's advocate through the whole of this. So apologies, Nvidia. But that's my natural state of mind. 4th gen ray tracing cores, so 360 ray tracing teraflops. Okay. AI management processor, Blackwell-based streaming multiprocessors with built-in neural shaders and 125 teraflops each. GDDR7 memory at 30 gigabits a second, support for DisplayPort 2.1, PCI Gen 5, and 4 NVENC decoders. Woo! Means
big chip, big spicy chip.
The thing is, it's funny because sometimes you just want a chip with the decoders if you're working with a lot of video.
Yeah.
Most of this compute stuff is just
yeah.
But yeah, funny thing, there's also some custom RISC-V cores in here doing management. Ooh. I mean, they've kind of had that for a while.
That's been a thing for at least since Turing, if I remember correctly.
I believe in the white paper. I believe in the white paper they highlight something new that's using RISC-V. So.
Oh, is there actually a white paper for or is there just?
I've got something that may be it. I don't know. I haven't looked through it all yet, so we're going to keep going through. Yeah. So streaming multiprocessor. This is what computes warps. And what we're looking here is Ada previous generation to Blackwell current generation. So that what they've done essentially is unify the floating point and the integer. So now every CUDA core can do every type of op, except for like super special function ops. But then you, sorry, go on.
Oh no, I was basically going to say, instead of having the 64 FP32 only lanes and then 64 lanes that could do either FP32 or INT32, all 128 lanes in the SM could do either FP32 or INT32 now. So
the thing is, over generations, they flip-flop between supporting all and doing a split. Because the reason why they say they do a split is because the workloads that they're seeing are such that you can weight them differently and save silicon by optimizing for that weighting. However, if everything supports everything, then you have a universal solution that it has the bottlenecks change. So yeah,
what's funny is in terms of everything being able, all the cores being able to do all the operations that the chip in theory can do, Pascal had in the SM 128, and this actually isn't an SM. This is an SMSP or a SM subprocessor. Essentially, this is a section. There's a later slide.
Slice.
I think it's a. I don't remember what SM stands for, but subpartition. So essentially, there's 4 of these in a SM. There's a slide for that next, but yeah.
And I realize you can't see me moving the mouse when I'm trying to point to stuff. But in the top right, you now have these neural compute engines inside the pre-shader compute. So that can do some light operation if you need to optimize what your compute is doing, which is this. So it turns out your workload, the way GPUs often dispatch work is that they bunch it all up into warps. And say for a single frame, you'll have 10 million warps of however many threads each. And they just fire it off almost, and assuming that there's no interdependencies, they fire them off all at the chip, all at big chip, all at once. And they just queue up and run and run and run. If you're smart, you'll make sure that some parts of the chip are used for neural rendering, Some parts of the chip are used for rasterization. And when there is dependency, making sure that those dependencies are local to each other so that you can leverage more local memory if you have to share data between them, especially when it's a global sync. So what they're doing here, what it looks like to me, is if you can organize your shaders between what requires tensor and what requires shader, you can now balance your GPU workload a lot better. Now, you could say, isn't this solved by numbering everything 1 to 10 million and then firing off 1, 2, 3, 4, 5, 6, 7, 8 in order? Yeah, yes. It would, but apparently that's slow.
Well, not just slow, that's a lot of power.
Yeah, because then you have to iterate a number 10 million times every time rather than just saying,
well, not
who's next, go, who's next, go.
Should be
who's
1, next? Then what should be 2, then what should be 3. Branch prediction.
Yeah, and this is like a reorder buffer, making sure that different operations are.
It's a bit different, but kinda.
It's reordering. It's putting things in the right order.
Yes.
Depends how much you trust. Yeah. And then we get to GDDR7, the memory. So the latest generation memory, running at a higher frequency but lower peak. Is that petajoules per bit? That's a capital
yes,
P.
It's supposed to be picojoules per bit, because petajoules per bit would be everything.
You're consuming the Earth's resources. Yes.
Yeah.
Yeah. But what they're saying here is normally we think of binary as 1 or 0, and that's obviously an idealized situation. But when you're running at high speed, sometimes you can introduce additional levels to signify more bits or more differentiated bits. So 1 and 0 is called essentially PAM2 because there are 2 levels, or NRZ. Yep. NRZ is the official name, but in the PAM nomenclature, it's PAM2. PAM4 is a natural evolution to that because you're essentially doubling the levels. And so now you get 0, 1, 1, 0, or 1, 1. But PAM3 is kind of like an intermediate layer. And the thing is, it transmits fewer bits per cycle, but because the tolerances needed for PAM3 aren't as tight as they are for PAM4, you can run it at a higher frequency. It says here lower voltage as well.
Yeah, so PAM3 is weird in that it's 1, 0, and -1.
Well, it's not really. What PAM3 is you have
that's oftentimes the bit representation of the levels.
Yeah,
which hurts my head.
What it really does is that it requires two transmissions to submit 3 bits.
Yeah.
So PAM2 and PAM4, you can submit a whole number of bits per cycle, per transfer. With PAM3, you required 2 transfers to submit 3 bits. I did a tape because Thunderbolt 5 uses PAM3. But it's if it's a more efficient energy architecture, great. The potential problem is that the peak bandwidth may be less than a PAM4 solution.
Yeah, I'm wondering when this will all just become essentially RF, just PAM32 in RF solution.
So PCIe 6 is PAM4.
I don't think they've actually decided that. So when I last looked at the documentation a week ago, they hadn't quite decided yet.
No, they have. It's been in the spec for ages.
Has it? Because I saw that I was seeing stuff that was saying that they were debating between, or maybe I'm thinking of DDR6.
You might be thinking of DDR.
Yes.
For PCIe, PCIe 6 is a PAM4 signaling.
Yes, I was confusing it with DDR6, which could either be PAM or NRZ, and I really questioned how they're going to drive DDR6 with NRZ.
But I've even seen PAM6 solutions for future connections. I mean, top level, every connection is a transfer of some energy levels.
Yeah.
So I've seen a PAM6 transceiver at a conference last year. I did a small post about it, and apparently the SerDes community blew up because I wrote a post on my blog about it, and I got a bunch of people out of the woodwork just add me on LinkedIn, and I'm like, wait, what? All I did was see this and go, ooh, shiny, but apparently that's enough to get whet people's appetite. So that's good. So 4th generation ray tracing core built for mega geometry. It's with ray tracing, it's always a case of realism versus compute and how you do it. We all know about BVH engines and trying to both minimize that workload but also get more bounces on your ray. So this is attempts to do that with fewer operations and either get the same result or a better result with a 4th generation ray tracing core. And as you can see, the numbers just saying theoretical 8x, the triangles versus Turing, while being 25% better on memory. Again, this comes down to throughput. And we'll get a little bit into that as well.
And I assume that the memory footprint savings is from exactly what we were talking about earlier. You're having to write less out to memory.
Yeah. The thing is, some people may think that, hey, shouldn't this be solved mathematics already? No, new ways of doing the same thing are happening all the time. New proofs for Pythagoras are happening today.
Yeah, I was going to say, there's no single right answer.
No. There's just the right performance for the right power, for the right ease of integration, which is on the game developer side. But yeah, so tensor cores, so not ray tracing cores, but this is what we mean by keeping data results local and then going through your operations. Here, ignore where it says FP16, FP8, FP4. That's just support. But with the Blackwell Tensor Core, you can now do 32 stacks of tensor ops before needing a memory output compared to Pascal, which could only do 1. The size of your matrix element also increases, which improves performance as well. And then you also put in FP4, which is a 4-bit representation numbers. So the idea here is that as gaming pivots more to machine learning as part of the pixel generation, whether that's guessed pixels, interpolated pixels, generated pixels, was it back at Computex? Jensen said 8 out of 9 pixels will be built by AI, built by machine learning in the future.
That sounds like something he said, yeah.
So I'm not necessarily talking about 1 pixel and the 8 around it. Also think forwards and backwards in time by multiple frames, right? It's that sort of principle. And the idea, part of the idea here is, and we'll get into frame generation in a second. If you're running at 60 frames a second native, but you want the effect of say 240 response, if you can generate a theoretical frame while the main one is being rendered, and it costs less energy, do you get a better experience? And Nvidia says yes.
So what was interesting was actually Jeff and I last night he saw some interesting not with regards to DLSS but with regards to RT and how there was ghosting in Cyberpunk 2077 of like the pistol that you're holding for one example, and you could see the ghosting. I was like, I don't have any ray tracing GPUs other than my XTX, so it was like, you know what, let's fire up the XTX and see what does it look like there. And it ended up being the same effect. And to me, that sort of brings up the question, would you rather have realistic looking graphics or in the form of it behaving like you would expect the real world to behave, or would you prefer graphics to behave, look more like the real world? I know that sounds weird, but
I think the word you're looking for is how comfortable are you with what's on the screen, right? For some people, that level of comfort is very wide because they don't mind stuff going. Maybe they don't notice the ghosting because they're not that observant, so they're happy with it. But for those people who are super dialed in, you might hate it. That's okay.
Yeah.
Turn it off.
Yeah, and yeah, that sort of gets back to
it's like back in the early days of this channel, I was heavily criticized for my audio, and to be honest, I still am because it's usually terrible. But my comfort level in audio range is quite wide. It turns out what I consider I'll happily listen to is like nails on a chalkboard to some people, right? And if that can happen with audio, that can easily happen with, graphics. So
what's funny is that, at least for me, what I will deal with in terms of audio is more narrow, but graphics wise, because I'll be honest, my eyes aren't very good, is a lot wider than a lot of people. Like, I actually don't notice a lot of stuff that people are like, how do you not see that?
Yeah,
my eyes are not very good.
My eyes are pretty good. My hearing is terrible. I do not have
the opposite of you.
Yeah. So going between these two slides, the simultaneous AI and graphic processor, this is where this AI management processor comes in, because it's actively looking at how long things are taking to process, what parts of the chip are being used, and where other resources can be utilized for other features. So in this case, frame generation, but also how to minimize delays, whether it's context switching between different sorts of compute, or whether it's the ordering of the compute. So and then Blackwell is designed for max Q. Q in this point is meant to mean efficiency, right? Rather than P is performance.
Yeah, Q is efficiency. Why it's Q, I'm not positive, but it's
silicon quality. There we go. Designed for quality. Hence why we have all these slides listed. So advanced power gating.
I mean, maybe they mean maximum quantum efficiency.
Yeah. Don't give them ideas. Don't give them ideas.
What's funny is that quantum efficiency is actually important in astrophotography, but for cameras.
Don't give them ideas. Power gating is something that over the last 15 years, 20 years that I've been covering chips has come on leaps and bounds. It's usually a trade-off between how much control can you have over discrete areas of the chip versus how much silicon it's going to cost to have that control versus how quickly you can go in and out of sleep states. There's no point having lots of control if your sleep to wake is a second, right? So this is all about if something is idle for 100 nanoseconds, can we cut power? And can we do it in a way that's repeatable? So this is if you've got a specific kernel in your shader that's taking up 80% of the SMs, but is memory bandwidth limited, while you're waiting for data to come in to fill the SMs, can you actually power the SMs down? And then recover that state when the data is ready, because you can't hide it with other compute. And every generation, it's getting smarter. Every company's got a bunch of ways to do it. A bunch of companies are leveraging third-party IP to do this. You may have heard of Protean Tex's, one of their features is to do things like this. It may also be things to do with advanced timing, rather than using quartz crystals, using silicon, using a company like SiTime, who I know is a partner with Nvidia on their switches at least. But the idea here is, yeah, how can you save the nanojoules every few cycles based on where the workload is at the right time? There is a thing in computing called a guardrail. So as you apply workload, you get a voltage drop due to the work. So you have to compensate by overvolting that drop, because you don't want it to go below Vmin, because below Vmin your chip crashes.
Turns off.
Yeah. But if you have good analytics, you can have a predictive guardrail as workloads are pushed through the pipe.
And this is, so the whole reducing that V droop is why a lot of overclockers change load line calibration, right? It's to try and reduce that droop so that if you're trying to run the chip at its absolute maximum, you don't dip below what is effectively your new Vmin.
Yeah. But the way load line calibration works is, instead of having your potato gun firing horizontally and falling, you fire it up at an angle. So it means you're technically putting more voltage through to counter the drop.
Yeah.
And that's your calibration. But if you're smart, you can adjust load line calibration on the fly, because you know the workload that's coming. So yeah, basically this this graph.
Yeah, that whole slide.
Yeah, so the difference between the dashed line and the solid line is your power saving between active and inactive. But the point is, yeah, this is microsecond level adjustments.
Yes.
And frequency switching. So this is a bit of a double-edged sword, because yes, you want to reduce frequency to save power when you can. However, that can introduce workload consistency rather than keeping it at a flat frequency. And one may argue that in a gaming workload, saving every millivolt isn't necessary all the time. So why not run at a fixed frequency and a fixed voltage regardless of the workload? But then being able to come down to a super idle rather than over predict and go beyond what you need to, just because here, if it's like 2700 megahertz, but you're idle, 2700 megahertz at idle still isn't doing any work.
Yeah, you're just burning power, feeding the clock tree essentially, which, by the way, is actually trying to get the clock tree power down is actually a big thing in the industry right now, because the clock tree can actually eat a not insignificant amount of power.
So this is being able to distribute your voltage and your frequency around the chip where needed.
This is also keeping the clock, keeping 100 megahertz consistent from this edge of the chip to this edge of the chip.
Yeah.
Or in a chiplet scenario, from this chiplet to this chiplet, right? So it's not a trivial problem to solve.
That's why you have phase lock loops. And I know there's one company who is helping AI chip companies with asynchronous clock meshes to get around that issue.
Interesting.
But you obviously you end up with buffers in places and stuff. I don't know the exact technology, but they'd speak to me if I asked, I think. Display and video. The key thing here that I saw from reviewers, aside from DisplayPort 2.1 up here, the 20 gigabit per second, is in the bottom right. We now have 422 AV1 decode and encode. So for people working in higher definition video and high bitrate video, but more of them as well, because you get more decoders. So that's all good. And then multi-frame generation. So here brings together a number of key features, which is in another slide deck. So let's see if I can get this slide deck. Is it in this one? Generative AI for games? Or RTX Neural Rendering. Let's see if I can put I'm going to put a poll in YouTube chat and say, what do you want to read? Because depending on time, we may only get through one. Which slide deck do you want? What are the options? RTX Neural Rendering or AI for games? Is that the other one?
Huh. So apparently they didn't have the full.
Check.
I thought it was in this slide sheet, but apparently not.
It's I think
it's in the there's a separate PNG in the file that you sent me that has the whole SM. But actually, before we moved on to that, I would like to talk about another architectural change, tensor memory.
Go for it.
So tensor memory, there's actually a nice little image in the link I sent you. But basically what this is that this is a 256 kilobyte accessible memory. We don't know if this 256K of memory is actually separate like structure on its own, or if it's actually a shared structure. But the way that this works is that it's essentially a 256K scratch pad that each tensor core has access to and can write and read from. And this improves throughput of those really low precision but high throughput data types like FP4. And I really wonder how they're implementing this in hardware. Yeah, there it is. As you can see, essentially.
Where did it just go? It doesn't like me zooming in.
It doesn't like scrolling. So on the
they go too high or too low?
No. So on the left,
yeah.
If you see 9.7 point, yep, there you go. Yeah,
so just to clarify, this is the PTX manual, which is NVIDIA's manual for its low-level compute architecture.
Yeah. So I have a question here that I don't know if will be answered, but how exactly is this being implemented in hardware? So the reason why I ask that is if this is a separate, like an independent structure of 256K of RAM per tensor core, there's 4 tensor cores in an SM, so 1 megabyte of cache per SM. There's, I believe, 192 SMs on a GB202 die. That's 192 megabytes of cache, or SRAM, really. Where is that?
Where is it?
Yeah, because that's even bigger than the L2 for
So the tensor core has dedicated memory for all tensor core operations, right?
Yes.
However, and this is the tensor memory layout.
Yeah.
It's dynamically allocated within a warp, so within a bunch of threads. So you can't share memory between warps.
So
it does say dedicated, but
yeah.
dedicated doesn't necessarily mean independent of what we've already told you.
Yeah, and I'm wondering if this may be like wave. I don't know. It's weird because my question is, where the hell are you stuffing it? Like, where is it fitting
Physically?
on? yeah, like where could it fit? So it's confusing to me.
Could it be compressed somewhere?
How? Like you can't just magically hide 192 megabytes of cache. Now, what I will say is if you look at SM, if you look at the top here, it says on architecture SM100, which what that means, so as far as if you go and dive into this manual a bit more, what you'll figure out is that SM100 is actually data center Blackwell and SM120 is gaming Blackwell. But
So
if you dig in a little bit more, again, the gaming Blackwell, even though it's not mentioned here, does support some of the tensor memory operations. So it may have partial support. I don't know, but this has been making me scratch my head, going, how is this working?
How many tensor cores are on the chip?
So it's 4 per SM, 192 SMs, so 768.
Yeah, 200 megabytes. Yeah.
Yeah.
And we're calculating that by 512 by 128, which is columns of rows, and then 32 each is 32 bits. Okay. Well.
Yeah. So
Or is it just in one of the cache structures and it's carved out?
Well, the thing is that it doesn't fit in any of the cache structures as like a whole block, right? Because it doesn't fit in the L2.
Does it not?
No.
What's the L2?
The L2 is 128 megabytes of L2 on die.
Yeah.
So
there must be something going on. Nvidia doesn't seem to speak to us, so we won't know. But we can go to that. Let me see where the poll is going. We've had 38 votes so far, and 82% want RTX Neural Rendering. So let's go with RTX Neural Rendering then. And it's this one. Okay. So session 1, RTX Neural Rendering. Programmable shaders. So the ability to do what you like in a small compute kernel, which is nice for graphics. And yeah, okay, we've done some things over time. And now, arguably, this is a step function change because we do something called a neural shader, which brings together both the shader cores and the tensor cores. And then we end up with things like neural textures, neural materials, neural volumes, neural radiance fields. Okay, we get it. It's neural. Yeah, what's exploding inside my head right now? Neural.
All your neurons.
Yeah. So, and so, yeah, RTX neural shaders. So rather than just doing having RTX shaders, you have RTX neural shaders, which means you're applying some sort of machine learning, sorry, to your data, to the shader, and you're running a model that's been pre-trained on a specific workflow. That may be a game, that may be a scene, that may be, or as high level as an engine. So cooperative vectors, which will unlock the power of tensor cores and NVIDIA's GeForce RTX hardware and enable game developers to fully accelerate neural shaders on Windows. I almost read shadows on Windows. But hey, also you need neural shadows. Is that ray tracing? But yeah, the idea here is that with rather than needing a full texture, you can use a lower bit depth texture that is then brought into the neural shader at the same time the geometry is compute, and the output is similar, if not better, for less memory, right? So you do a small amount of training, you tell the neural shader what exactly needs to happen, and it will try and find a more power efficient way of producing the same result by using AI ops. So, did you see this spinning demo
No,
of
I
the
didn't.
chandelier? It looked really good, but it was pre-rendered, so it always looks good. But we'll see. So yeah, and we have the demo, and so this is another feature. So ray tracing, historically, we talk about how many rays per second. So if you've got a 1080p display, that's what, 2 million pixels. So if you have 2 million rays per frame, that means every pixel gets 1 ray. But if you need reflections and you need interactions between materials, then you might need that ray of light needs to have 2 bounces. So now you call that 3 rays per pixel. So you could say, oh, well, in order to get the perfect world-like representation, you need 1 billion rays per pixel, infinite, because that's essentially what happens in real life, right? Well, what if you could do it smarter? What if you could do some on-the-fly training with indirect rays to help your ray tracing? And that's what we have here with Neural Radiance Cache. So it's the how can you get environment elements that should interact with each other and get the result without doing the hardest computation needed to get the result with ray tracing. So trace 1 bounce per pixel, and with the right model, you can infer what other pixels in the scene you should be interacting with, rather than actually do the compute to calculate the line in the 3D space of the tech, and then calculate the exact texture that ray should be interacting with, and the exact pixel of that texture to be interacting with, and then do the collaboration with the right model, like a GPT trying to guess what the next word in the sentence is. It guesses which other pixels in the geometry space, or which other, not voxels, but you know what I mean, what other interactive points of textures in the space you should be interacting with, and optimize that live during your game. That's actually pretty, especially because this also reduces the workload and the memory requirements. That's actually pretty neat. I like that.
Yeah. Again, it's using essentially a self-training network, whatever that is, a CNN, a transformer, whatever model they're using, to again try and, because I know 10 years ago the thought it was always compute is cheap, memory's expensive. Well, now we're starting to hit a point where compute's expensive and memory's expensive.
Yes.
So
agreed.
Yeah, we're hitting sort of a limit where we are needing to reduce both memory and compute, which is a really weird place to be.
It's funny, right? Back in 14, I went to Mobile World Congress, which is the big mobile smartphone operator plus vendor plus supply chain related event, end of February, beginning of March in Barcelona. And there we met, this is me and Andre at the time, met with Imagination, IMG, which back then wasn't the post-Apple apocalyptic version it is today. But they were showing off a custom ASIC they designed in 5 watts, did 300 million rays per second. So at 1080p, you got 150 rays per pixel. And it was super realistic, super smooth for 5 watts. Now, obviously, that's 2014, we're 10 years later. Think how many rays we can do. Turns out that actually does burn a lot of power. And yeah, if you can do this, in frame, yeah, I like this. And even Warren here says this may be my favorite feature of the new stack. So people are saying they want their rasterized pixels. the idea here is that you're not going to notice because it makes the scene look better versus zero ray tracing. If you did a full 300 rays per pixel or 3000 rays per pixel, then yeah, you'd get the scene to look better. But now you're at 2 frames a second. Good job. Now you're playing Civ 7, sorry.
Oh boy.
Hey, it keeps asking me if I want to pre-order, and I keep saying no.
No. I was burned on Civ 6 on that.
They made it too complicated.
Yeah.
Civ 2, Civ 3, even Civ 5 were a lot simpler to understand. And so this is an example here of a texture skin, and you can see it's got a bit more reflectiveness on the top. So it's a bit more shiny. There is a bit more detail on the original. You can see in the like head crab fingers, but then also underneath this sort of red hand. I don't know if it's just because it's more vibrant, but I think there's a bit more detail on that.
Yeah.
But this is obviously comparing peak RTX with RTX Neural Radiance field. So I think realistically, you'd probably prefer the one on the left to the one on the right, but the one on the right has taken a lot less work to get there. So they showed a demo. Neural faces.
This I don't know how to feel about this. This is like weird uncanny valley levels of spookiness, and I'm uncomfortable by this, honestly.
So I have used an AI generated persona in one of my videos. Nobody knows which one. It's not of me, funnily enough. But so the whole point of having a machine learning generated, the VTubers who do this obviously pick weird, fun animation type kawaii whatever. But this is meant to be realistic, right? So if you could do that from a realistic standpoint, the person who showed me that imagination demo all those years ago now works for a company called Synesthesia. Not Synesthesia, Synesthesia. And their business model is that they have a set of AI avatars. That's the word I was looking for, avatar. And you can do text to voice for use in presentation material. The idea being, if you're building a company and you need to create a standard set of informational instructional materials for your software or whatever, rather than hiring an actor, get a studio, make sure everything's synced, make sure the audio is great, retake if you need to, go through the editing suite, you essentially rent one of these AI avatars to do it for you. And the idea is it sounds human. The intonation is human. It can come across as a little bit stiff because there's no sort of like arm and shoulder. It's a technology that's improving. However, you pay some amount and you get so many hours a month access to their system unless you want a business account. However, for $1,000 a month, they will convert you to an avatar. So if you wanted to have an avatar of yourself for videos, such that if you were on a plane or you didn't have your equipment, but you still wanted to create content, you could write a script, put it in your AI avatar, put in B-roll, Bob's your uncle. Or Bob's your teapot, whatever.
No. Maybe as an April Fool's joke, maybe.
Right, so the feature of like background blur, but then also eye gaze correction, right?
Okay, the eye gaze correction stuff still, like, to me is Uncanny Valley, and it doesn't feel natural. Like, nobody directly stares into the camera looking straight at, like, unless you're doing like a very specific video, like you don't stare into a camera. Just
I've done one of those.
Dead looking straight into the camera. No, you look around. You look to your left. You look to your right.
You're human.
Just having your eyes just straight to the. It's weird, and it's.
So
I don't like
right.
it.
There's also, you know, beauty filters to get rid of all the pock marks and your brown teeth. You know, I use a beauty filter on most of my videos because I'm goblin. But also, imagine if you're super goblin, as in you've just woken up and you need to go into a meeting. You're in your string vest and your pants and you haven't shaved and your hair's a mess. Why not stick up your AI avatar that looks like yourself for your professional business meeting? You will still speak for yourself, but it will make the mouth go with your movements for it.
Yeah.
As Zio says, maybe it's for apology videos only.
When will it start playing the ukulele too?
Yeah. You know. And Warren says, combine this with a 3D model of a conference room at your office, then go to the beach. Yeah, you can. Yeah. It won't hide the flush. Probably, actually, with noise cancellation, maybe. But that's sort of bathroom echo. Yeah, maybe. But it's, you know, I already have a service I use to generate my voice because sometimes I'm in a pinch and I need to do voiceover B-roll and I'm not in a position where I can record. I've done that on video segments up to 40 seconds before. And nobody has really noticed it's quote unquote machine learning generated, that it's not me. And these services, when I first used them, yeah, it required some tuning to get right. Now it's really easy. I mean, you've seen the video of Jeff Geerling where his voice got taken by a embedded Chinese company for their YouTube videos. I mean, they were great in the fact that they took them down straight away when they were alerted. But now you only need that with like a minute of audio from someone to do that. So yeah, this is just the next stage beyond, and eventually you have Second Life. Yeah. We'll see.
Second Life.
But then it uses 80% of your GPU to do it. So, yeah. The thing is, this is obviously clearly a fake photo. When it hits super uncanny valley, you know, the catfishing level, that's perhaps when it gets worrying.
This still is strong uncanny valley for me.
So hair. Ray traced strand-based hair is expensive. Fun fact, one of my most favoritist films of all time, Final Fantasy, The Spirits Within, major flop in the cinemas. It cost Sony and Square 150 million to make. All the hair on the lead person's head, Dr. Aki Ross, I forget how many strands it was, but the cost to model and render just her hair for the entire film was $9 million. And this was in like 2002. Let's Final Fantasy Spirits Within hair cost. Yeah, it cost 137 million. It only made 84. Yeah, I'm pretty sure it was something like $9 million for the hair. I read it in a magazine. Surely it's real. Yeah. The film's budget was high, with a large portion likely dedicated to achieving the realistic visuals, including the complex hair animation. The thing is, I actually thought the film was really good. But I also loved Final Fantasy VII at the time, and Final Fantasy VII Retrograde is, I think, was released today. That's remake. Is it Retrograde? Is that the second installation? Integrate. Everybody loves Final Fantasy VII, but the point is, you can do a lot more today. And if you ray trace it, it's really annoying because the rays bounce around in the hair as well. If Rebirth, there we go. So what we've got here, 3D triangle tubes with 6 triangles per linear segment, so 6 million triangles per groom. Instead, you do linear swept spheres, so you essentially create a Bezier curve between essentially the joints in the hair. It's 3 times less data, and it's better for ray tracing. I wouldn't have thought that would be the case, but huh. Is it because you only see the spheres? I don't know.
Maybe.
Just to correct, my shorts are not AI yet.
Keyword yet.
If it works, if it you know. Maybe I'll phone up my guy at Synestia and see if he'll sponsor a few shorts. But then he'll just say, yeah, great, you sponsored 6. Now, if you need to use it, you actually need to pay $1,000 a month. But yeah, we all know that geometry is increasing. Whether it actually needs to for the game itself is another question. Ray tracing, we've got your BVH structure going down to triangles and a mesh. This has all been said a million times before. We can get into, you know, the improvements. Here we go into clustering, which was the next update. We've also got tessellation involved in here as well as an after effect. But in terms of, so LOD is a term called level of detail. In a game, when you're just doing a first-person shooter, if the person's right in your face, you need the maximum amount of detail, right? You need maximum triangles, maximum fidelity. If they're the other side of the map, but still in view, maybe they can be replaced with 10 triangles.
Yeah.
And then in between, you'll have different varying amounts. And this is what we call level of detail. The further it is away, the fewer triangles you need to render, therefore the better your performance. And because it doesn't affect the gameplay. This is why Battlefield, I want to say 4, had major problems because they were rendering the water under every map, even maps who didn't have water. So if you don't see something, maybe you don't need to render it. But if you also don't need to see something,
ocular occlusion has been a thing since time immemorial.
Z-culling. Yeah, it's that sort of thing.
It was Crisis, not Battlefield, that did that.
The new Crisis. I thought Battlefield, one of the Battlefields did it as well. But yeah, it's here. You're saying if you've got a big model, maybe you don't need the same level of detail across the whole model. And by having clusters, you can have your level of detail differ across the texture map of the model. And they went into some demos, and we're talking about RTX Remix. This is where they're upscaling old games with RTX tools. Okay, so then we get into the second part of this presentation by Brian Catanzaro, VP of Applied Deep Learning Research at NVIDIA. He actually just had a really great interview with Digital Foundry. And I want to get him on the channel as well because I actually bumped into him at CES. I recognize the name, but I didn't know the face. He saw me introduce himself to me. I'm like, hey, yeah, you're that guy. Yeah, that's cool. Within 2 minutes, we were hitting it off. He's a really smart dude. He understands his purpose. But he also was explaining things in very simple to use English, and I also, he can also go very, very technical. So he'd be great to have on as an interview, speaking about where NVIDIA is going with machine learning based gaming, because I don't want no fake frames, man, is apparently what the internet is saying. So yeah, this is, so this is his slides. 3 pillars of real-time graphics: frame rate, responsiveness, image quality. Pick one. Which would you have? Yeah, you can't have one. You need at least 2.
Yeah.
But the point here is that, sometimes that volume is fixed and you reduce image quality in order to get better smoothness and responsiveness. We know this. You reduce the resolution and you get better performance, but it looks worse. So, but if you had 10 GPUs, SLI.
SLI will make a return eventually, right?
Yeah.
Right, guys? Right?
So, but yeah, imagine you could have 4K at 250 in 35 milliseconds. You might be playing League of Legends. But the whole point here is that perhaps they can do this with machine learning on one GPU. This is why we have DLSS. And this graph here is just showing the adoption of DLSS. So this is deep learning super sampling. This is the ability to take a lower rendered image and upscale it into a higher resolution image, but have the quality of the higher resolution image. So deep learning, super sampling. And yeah, it's saying 540 games and apps. Apps is a bit of a cop-out. 15 of the 20 top 2024 games. Hands up if you played. Actually, I'm going to stick a new poll in here. Did you play a top 20 game for 2024 in 2024? Yes, no. What you define as a top 20 game, I guess, something that probably cost more than $50 and was labeled AAA. Right? Because there's this continuous argument about most people still play games that are 5 years old today. But they're saying 80% of players activate DLSS. I wonder how much of that is just simply that's the default. So activate implies a conscious decision to enable. So, and then 3 billion hours played with DLSS. So there's that. Yeah, it's been going on for a long time. You train a model for a specific game or features within a game, and how applicable is it? And this is going through how models have changed over the years in terms of just general machine learning. In the beginning, there was convolutional neural networks, and they could tell you whether an image.
In the beginning, there was cats,
and then there was convolutional neural networks.
Yes,
that could tell you that what you're looking at is a cat sometimes. And then you have transformer models that can provide context. The thing is, actually, I want to bring up that tweet. Did I copy it here? Jensen giving me lunch.
I assume that this was a generated image.
No, this is real. Let's see if I can share the screen again.
Oh, yeah.
This is Jensen and me. That's Goto-san from PC World. If you understand Japanese, go read his stuff. He's really smart. And this is Paul Alcorn from Tom's Hardware. Paul's really smart. Tom's Hardware isn't. And this is him in 2018 because the NVIDIA press conference was delayed at lunchtime at, was it at CES or Computex, handing out sandwiches, and I was first in line for a sandwich. Yeah, people asking about the Elden Ring DLC does count. Technically, Balatro was a top 20 game.
Oh,
Shoot.
well, then technically I would have to say yes, but
right. But
honestly,
this is so.
Honestly, to me, Balatro, Slay the Spire is still number one, and FTL of the roguelites.
But this picture is from 2018, right? I looked a lot younger back then. But if I go to the article where that was taken, this is the Computex NVIDIA press conference. Very different to what we have today with stadiums and 20,000 people. And just stuff on display. And yeah, here we go again. Yeah, there's the Jensen picture. I haven't had lunch. The sandwich was green. I haven't had time to eat it yet because the minute he gave me lunch, we were ushered in. This is the one of the first machine learning platforms with V100. That's how old this is. Yeah, this is Xavier or Pegasus, and the V100. But the reason why I bring this up is obviously this is not a $3.6 trillion company at this point. And he's talking about gaming. Gaming was number one. This is then we have CUDA, then we have compute engines. We're still talking about 32-bit operations and 16-bit operations. Single fastest chips, fastest single node, fastest scale with Volta, DGX2, and here we have first generation NVLink and dual Xeons and 3200. 10,000 watts for 16 V100s. Those were the days, eh? All these different variants. But the reason intelligent machines, we have Xavier. So this is a chip with a VPU, a deep learning accelerator, very specific dedicated compute for, this is self-driving. DLA is NVIDIA's version of the TPU.
NVDLA. Yeah, well, I mean, DLA is still around.
No, I know, but he's taken the jacket off because it's too warm. This is the first Isaac platform, built in 12 FinFET, robotics platform. But this is where he had the first I Am AI campaign, announcing Taiwan supercharging AI with NVIDIA, a 10-year collaboration. And that was the end of the presentation. It was convolutional neural networks, really early. A focus on manufacturing, healthcare, smart city, and transportation, a 10-year collaboration. I wonder if that's still going on, but with Blackwell.
Potentially. I mean, if it was a 10-year collab from 2018, then yeah, it'd still be happening.
TPU in this case means tensor processing unit. It's what NVIDIA calls its AI chip.
Well, that was the Google thing, was TPU.
Sorry, yeah, that's what I mean. Sorry. What did I say?
You said NVIDIA.
No, I meant Google. When can we run 4K 120 hertz on a single card? So this was when is Volta coming to gaming? This is before Volta came to GeForce.
Well, Volta never came to GeForce.
Oh, there we go.
Turing.
But yeah, this is the reason. I bring that up. Let's go back to the slides. That one. No, was it that one? Have I lost my spot now?
No,
that one. But what I'm trying to say is, back then in 2018 is when we were having CNNs and we were talking about, will AI ever be able to determine that there are two things in an image and how they're interacting? And that's what Transformers enabled. So just a bit of history on Transformers. Yeah, that was a stupidly long segue. But now we have Transformers in DLSS. So previous DLSS was using CNNs. Now, CNN models are smaller, more compact, and run a lot faster. But the level of accuracy is super limited, and you can't do these sort of multi-location interaction points within a scene, because it just does one thing. It does one thing really well, like identify human, and then it puts a box around a human. You've seen the whole CNN VPU type demos that companies have done. So now we can say, what can we talk about in a scene that's interactive with each other, almost like the neural radiance fields a little bit. So this is how do we reconstruct rays with a transformer model rather than an old CNN model. So this is DLSS3, this is DLSS4. And then same, and you can see here with the transformer version, there's a lot more integration with the leather being pockmarked and where it's, you know, bending, and you can see a little bit more of the again, I realize you can't see where my mouse is pointing to, but on the edge of the bag at the seam, you can see there's a lot more detail in the interaction in there, and that's the point here. So previously with DLSS3, you'd have the frame generation, you go through an optical flow accelerator. This is just determine how pixels are moving through a frame. And then you'd use that, and then with DLSS4, you use that information over time to generate more frames and smooth out your experience. So you have your traditional render, which may be a 1080p. You then super resolution it with ray reconstruction for 4K, and then you generate 3 more frames off of that upscaled 1080p image. So when we say 8 out of every 9 pixels will be machine learning generated, here we go.
Well, this is 15 out of 16 pixels. Yep.
Yep. Going from 27 FPS to 200 FPS, I saw in some circumstances. And the whole point here is that these frames still take a variable amount of time to compute, and you don't want to just push them out when they're ready. You need to pace them properly. So they've also got this new feature called flip metering, which is, you know, some additional smarts in the hardware and software to do this. So you get your frames at exactly the right time. You obviously need some sort of G-Sync or free sync in order to get the best out of this, depending on your frequency of your monitor as well. So it can leverage that, as far as I understand. Yeah, and here we go. 27 FPS normally, 248 FPS with what looks like some might say a better image or a near perfect reconstruction. So, and yeah, this is a bold claim.
Well, not just that. One of these games is not like the others.
Well, Hogwarts Legacy is shit. Black Myth Wukong is over-engineered. Alan Wake 2 is super old, isn't
it? Well, no, but of these games, 5 of them are FPSs. One of them is a strategy game.
Oh.
Like, it's an RTS. Frostpunk 2 was an RTS. Like, you don't need the highest frame rate. So
but the argument here that I've seen a lot of people make online is that if you're doing frame gen, your by the book FPS does increase. However, because typically FPS increases are meant to give somewhat linear improvements in experience, this is a non-linear improvement in experience. And realistically, wouldn't it make sense this to be more related to games where you basically want to go from 30 FPS to at least over 60 if you get the benefit of the responsiveness. You don't need to go to 300.
Sure. But it was more that Frostpunk 2 is not really the sort of game where...
Yeah, ignore Frostpunk 2. Just focus on the technology.
Yeah, I would agree.
Yeah, it's this might be one of the things you actually have to experience. So, I mean, Raphael says latency goes up, but not by a ton. NVIDIA's argument here is that latency is actually going down. because you're doing super resolution with path tracing as well. And you can pace frames at a proper rate. So it's at 27 FPS, you're at a non-integer multiple of your display. Whereas as you go above 60, you can now optimize your frame allocation. You're pushing it through the buffer at the right time to minimize that latency. Yeah, apparently support for 75 apps on day 0. Your mileage may vary. Satisfactory 1.0. Does that really need DLSS? Yeah, the thing is, the way these things get adopted is the minute there's a button for it in Unreal. But because DLSS requires training a model on that specific game, that's where some of the delays are. So NVIDIA's probably had to go out and pay some money to all these vendors to get all the data they need, especially for games that are still, to be released or have only just come out. I saw a report on a website saying that some models in this set have been in training for 6 years in some form or another. So
interesting. Wouldn't surprise me. I mean, probably that would be DLSS 1, like any games that try to support that. And yeah.
Gunny asks, when is day 0? Day 0 just means essentially they're ready before the chip is launched. But you're talking about like 1 second before the chip is launched, right? Realistically, when the chip is launched, it's day 1. So if you have day 0 drivers, it means the driver is ready before the chip is announced or before the game is launched, that sort of thing. So, and now we have also overrides for games in the NVIDIA app. I still don't have the NVIDIA app because you still need to sign in.
I thought they removed that requirement.
Oh, I haven't heard that. So I still haven't installed it.
I'm pretty sure that requirement is no longer a part of the driver stack anymore.
The more you know. And yeah, DLSS features. So DLSS4, everything will be on 50 series. Individual frame generation will be on the 40 series as well. Ray reconstruction, super resolution, and deep learning anti-aliasing will be available all the way back to the 20 series. Oh, okay, so I can use it on my 2080 Ti. Then we have NVIDIA Reflex for increased responsiveness. So this is when you have DLSS, but you also want lower latency, a better motion to photon latency as well, by optimizing the pipeline by having. So the point people often wonder, you don't need more than 60 FPS. Why should your game run at 120? The thing is, it pulls your mouse at 120, even if all you can see is 60. So imagine curving a arc through space and dividing it up into 60 points. Now divide it up to 120, which more accurately showcases how you moved how the arc was drawn. It's the same when you move your mouse, right?
I mean, this has been a thing on phones for years where the actual touch, like the touch sensors or the touch input is
polling rate.
240. The polling rate is 240 hertz, whereas the screen is 90 or 120, right?
Yeah.
So
yeah, and so that's always been a thing from day one. So even if you're playing at 60, if you run at 3000, you have a more accurate movement in what you're doing. You might argue, what's the point beyond a certain amount? And yeah, okay. And then we talk about how fast you can move your mouse in terms of inches per second, and such. But then we have in painting with predictive rendering. Exactly, I need to look up on that.
Basically, it's the signage in the background can be generated via essentially AI and model.
Is this Battlefield 2142? Let's put ads in to the game and change them over time. do you know how many times I played Battlefield 2142 easily 500 hours. I was in a clan. I can play competitive matches. I was no good, but I had fun. That game, you're in the wasteland, or you're in abandoned towers, post-nuclear apocalypse, trying to shoot down a tank, and off to the side is an advert for Intel Core 6th Gen. And like, Jesus Christ. And, I mean, you might think, oh, period appropriate. It's EA. They will advertise anything. If anything, their advertisements will be period appropriate. It's just, yeah. So, though, to be honest, if you're in the middle of something like a Duke Nukem 3D, and you get an advert, a live advert for Trojan, that's kind of funny.
Chat is correcting me. In painting is for when. So actually, what it is if you look at the gun, the white stuff around the gun.
Right.
That's the in painting. I thought it was the stuff on the background.
Okay.
Like the stuff on the screen. My bad.
No worries. I like talking about ads. I like talking about stupid ads anyway. And then Reflex 2 coming first to 50 series, then later to all the other GPUs. There's some Valorant. And then we have the full RTX kit. These are all the features. And that's the end of the slide deck. And we've been speaking for an hour and a half on all the features. For those of you who are wondering if there is a white paper, there is this, which is a this is just an architecture overview white paper. That apparently needs to be updated, and it goes through a bunch of the stuff that we've done, though in text, and they obviously put their own phrasing.
Can you go back a little bit?
Yeah.
One more. Okay. This is like the technical brief from Data Center Blackwell.
Yeah, this should be made public soon enough if it isn't already.
Hopefully there's more information that gets filled in here. That would be nice.
Yeah. And with that is Blackwell and the 4000 series.
Well, at least the end of gaming Blackwell.
Yeah, there are a bunch more slides here, and here's about AI for gaming, and perhaps that's a separate conversation we can have. But that was a big topic, and I realized that we actually wanted to say a lot this show. So I'm going to go straight into the second topic, and we might miss out the other topics and save them for next week. I know you want to, but you've got more to put out on your MI300 stuff.
We're done with
okay.
We put out all the info, so I do want to cover it.
Okay. So Stargate. This is a new announcement made by a mixture of new administration, Sam Altman of OpenAI, of Larry Ellison of Oracle, of Miyoshi-san, I always get his name wrong, of SoftBank. And if there's one thing the US needs, it's more AI, specifically more AI infrastructure. You may remember that Sam Altman 2 years ago was asking for $7 trillion to build the AI cluster he needs for the next generations of GPT. This is one step on that path. It's not 7 trillion. It starts with 100 billion. The money is being raised by SoftBank. There is a Abu Dhabi-based investment fund called MGX involved. Oracle looks like they're the ones that are building the data centers and or managing them. Apparently, there's one already starting to be built in Abilene, Texas. And OpenAI is essentially the company that's going to use them. So this is a big OpenAI project for them. And to be clear, this is OpenAI, not Microsoft, because Microsoft did put a bunch of money into OpenAI. Satya Nadella, the CEO of Microsoft, said he doesn't know where the money for this project is either coming from or going to. All Satya knows is that the 80 billion capex spend he's said for 25 is allocated, and that's what he's happy with. So whatever Stargate are doing with this, it's a new company which intends to invest 500 billion over the next 4 years to build new AI infrastructure for OpenAI in the United States. Read data centers. They say they have 100 billion ready to deploy immediately. This has been interpreted to mean during 25. Elon Musk doesn't like Sam Altman and thinks that they only have access to 10 billion and thinks it's a joke. Sam Altman has invited Elon Musk to come visit their facility in Texas. So the idea is that this will secure American leadership in AI, create hundreds of thousands of American jobs, and generate massive economic benefit.
So, okay, I'm going to play devil's advocate here.
Please do.
Regardless of if AI actually goes anywhere in terms of actual like AGI and like what people keep saying that it's going to become. Building data centers with the level of storage that is needed for AI, regardless of if it's actually used for AI in the end or not, will be used simply because the amount of data that's produced with or without AI at this point is becoming is exponential. So
in sorry to burst your bubble, but I've had many conversations with investors on this in the last 2 days. None of them have mentioned storage.
No. But I'm saying my point is for AI to work, you need a lot of storage, right? You need a lot of flash storage.
You need a lot of data. Yeah, again, nobody's ever talked about that ever being data. Yes.
Yes, but you're missing my point, Ian.
No. I get the point. You're talking about the physical SSDs.
No, I'm talking about even if AI doesn't become what people think it's going to become. Let's say it somehow becomes a big flop.
Yeah.
Regardless of if it is a flop or not, the physical data centers and the physical storage needed, regardless of the GPUs, right?
Yeah, that's what I'm saying. The SSDs
will still be used because the amount of data that's produced, regardless of AI or not, is insane and exponential. That's my point.
So out of the top 25 things to talk about this project, that is literally not on the top 25.
That's what I think.
It's the investors I'm speaking to are wondering what's the infrastructure, what's the supply chain on this? Is it real? Right?
Sure.
Data centers don't pop up overnight.
I'm assuming it's real, right? Otherwise, what's the point of this?
Well, this is what I'm getting into. You need, in order to build data centers, you need plans, you need workloads, you need ideas. One criticism was leveled, I think, by Dylan, saying most of the investment this year for this project will literally be in land and permits and shells, data center shells. Because on top of this, you also, as people have said in the comments, you need power, you need water. Why is Microsoft talking about restarting 3 Mile Island? Mobile nuclear power stations aren't a thing yet, as much as people want them to be. For 500 billion, are they going to be using Nvidia? Are they going to be using something else? What's going to be the right architecture? the lead times on this hardware. How much is it going to be? Where are they going to be buying it from? Who's going to be which PCIe controllers are they using? Because this would increase their revenue, or timing circuits, or these are the conversations I'm having. I made the point in one of those conversations to say, this is a private investment thing. However, they decided to announce it at the White House. And the president has said this is a private thing. However, if the government is going to get involved, then there may be tax breaks or reduced friction in getting permits, or reduction of wildlife laws so they can build a power plant or a base station and make it easier. I mean, everybody under the sun, not just these companies, are building data centers for AI. And it's a case of they're proliferating so much, and they're all gas backed as well, realistically. No matter how much solar farm you put next to it, the backup is always a gas power station down the road.
It's a gas turbine. It's so, for you guys who don't know, a lot of the emergency, so you have peaks and troughs. And if you ever go above your maximum capacity, there are specialized turbines that are designed to spin up in peaker plants, right? They're designed to spin up in, I think, 5 to 10 minutes, which for a massive turbine is insane, but they're insanely inefficient. But they're only used for a short period of time.
So load
and then
leveling.
They're shut off. And then they come on, and then they shut off as needed.
Well, these are just massive iron bars that rotate, right? Realistically.
Yeah.
And so and the president also spoke about these potentially being self-sustaining off-grid power deployments, and obviously Musk is trying to do his Colossus XAI thing, and have a bunch of Tesla batteries as backup power, right? Whether it's a supercap type or whatever. And so this announcement is very much, so ARM is mentioned, but we're not sure in what context. NVIDIA is mentioned, and realistically only to help with the co-design and also sell the hardware. None of this money is to Foundry, except to buy chips from TSMC. So it's this does seem pretty pie in the sky, and it comes back to Sam Altman being quite effervescent in his description and often requirements. Some may argue that's how he got to where he is today, by being that. Hundreds of thousands of jobs, I think, is more of a, if this works long term in the 50 years time frame, not as in construction and running.
Now, so again, to sort of, even if the whole AI thing goes bust, if they do build more power infrastructure, great, awesome. Especially if it's all nuclear, great, awesome. I'm all for that.
But this is in Abilene, Texas, to begin with.
Yes, but
it's Texas
actually connecting their grid. If I remember correctly, Texas is connecting their grid to the rest of the U.S. to prevent what happened in 2021, 22. I don't remember.
But again, if these power delivery are going to be essentially just for the power state, just for the data centers themselves, then it'll be a case of, if the data center ever gets discontinued, the power station can stay up and go click on the grid now. We'll see. Yeah, because of the size of the number, 500 billion, it's got a lot of investor interest about who the players are going to be and who the supply chain partners are going to be. I think they are already building a first facility for it. The proof is going to be 3-6 months down the line. Exactly how
I would even say 12 like
no,
depends on the permits and all that.
No, not about that. It's about the other funding from other sources they can bring in. to validate this project from even getting off the ground in the first place, because then you have to go buy GPUs. And I made a comment on one of my calls saying the demand for GPUs now is so high, nobody's buying them at list price. Everybody's paying because there is no list price really. Right. So are they paying 20%? Are they paying 50%? Are they paying double? Are they paying triple? Are they paying 10x? Because the point is, you buy a GPU, you buy a Blackwell. It'll probably sit in your data center for 5 years. Can you identify the value, your ROI of buying that chip over 5 years? And if it's 20 times the base price of the chip, are you happy to pay 2x? Are you happy to pay 3x? Probably. But that's when the investors come in and really you're actually spending investors' money. So, yeah, we'll see. Davina says Nvidia got rich from crypto mining. They've made 100x on AI already. So, yeah, they can always buy more power from Canada. That's assuming they don't invade them first. We're going to move on to this topic. Let's see if I can share this tab. Yeah. Hey. So, George, this is all you. So I'm going to ask you 2 questions to begin with before we get into this topic. Number 1, what is AMD's MI300A? For those who haven't heard of it before.
AMD's MI300A is, I believe, actually the first picture on there is of the sort of blow up image. But what it is that yep, there we go.
I was looking actually for a picture of the chip, but I told you to put one in. Like, keep going. What is 3?
So MI300A is, you know how AMD has consumer APUs? Well, this is a data center APU. What this is this is 3/4 of a MI300X paired with 24 Zen 4 cores at 3.7 gigahertz. That is backed with 256 megabytes of Infinity Cache, or MAL, which is then paired with 128 gigabytes of HBM3E, providing up to 5.3 terabytes per second memory bandwidth. This is taking the APU and bigifying it, essentially, for HPC workloads.
So question 1B, is this the ultimate console chip?
If it had display outs, maybe. And if it could rasterize, maybe, but it can't. It's compute only.
So modern console has 8 cores. This is 24. Modern console has how many compute units?
52?
6?
56, 52?
Strix Halo has 40.
It's 40, yeah.
This has 384?
No, this has 228.
228. So you have 3 times as many cores. You have 3 times as many compute units. You have 16 times more memory.
Yes.
Which is 20 times faster than a console. Oh, it's you know, I held up this last show, which is the Zen 2 based Xbox Series S.
Picture.
No, what you have to do is compare this to that.
It would be a slaughter. It would be a slaughter.
Okay, so this is MI300A compared to MI300X, which is the AI the AI chip. And the A here stands for APU. So again, question 1C, I guess, is Why haven't we heard much about the MI300A from AMD?
So MI300A is more towards HPC than AI. This is the chip that's powering the world's biggest supercomputer, El Capitan. This is, and some people would say, oh, but it can do AI. But frankly, if AMD wanted to position it to the AI market, then what they would have done is refreshed MI300A with an MI325A with 256 gigabytes of memory, just like MI325X. But they didn't. This is, again, not, it can do AI. It's not really meant for AI.
It's meant for HPC.
Yes.
So again, why haven't we heard much about it?
Because AI is the rage. AI is what brings in the big dollars and the big headlines.
So my argument would be, even if AI wasn't around, we still haven't heard much about it. Why would that be?
I think this would, I would say that this would be more talked about if AI wasn't as big of a thing.
My opinion here is that AMD made this, it's a variant of the AI chip with CPUs for very specific customers in mind. Anybody can go out and buy a 300X, realistically.
Yes.
You have to be a specific institution with a specific install to be able to obtain these.
Well, no.
Yes.
At first, yes, but currently, if you have enough money, you can go on eBay and buy one for 135K. Okay. So no, you can go buy one.
Okay, 135K. I stand corrected. I stand corrected.
But hey, I mean, you laugh, but okay. We were talking about how many billions earlier, so.
Okay, so question 2. Because you have an article about this, and
yes.
there's more than one. We'll get to that in a second. How did you get it? So I know you don't have
125K, don't you know? But no, massive thank you to Gigabyte and their Launchpad platform, which allowed us access to MI300A for testing. Without them, this would not have been possible at all. So massive shout out to them.
Correct me if I'm wrong, but there was, even though Gigabyte and their Launchpad program had given you access for like 2 weeks, if I remember correctly, you told me.
2.5 weeks, yeah.
Yeah. AMD wouldn't speak to you about it.
So that's
due to some complex internal
we were
politics.
Unable to get sort of assistance with some of the tests because of certain contractual agreements. So we were on our own in terms of actually the testing.
So because I mean, you've tested MI300X. That was a free-flowing exchange of information with AMD. But because AMD has this contract to a national lab, they were unable to discuss many things.
So MI300X, even that, while I did reach out and say, hey, we're seeing this stuff, they actually didn't get back to me in time for publication. So
oh, right.
So there was no exchange of information there. Again, that testing was done on our own.
Okay, so but that was more a, we don't have anybody to answer you right now, not a, we can't answer you because of other.
Yes.
Yeah. Okay. So you have MI300A. Actually, I did have a picture I wanted to share. Because I have it here. Let me share this tab.
Actually, that's the Gigabyte server. Well, it might not be that exact one.
This is what we saw at Supercomputing.
Supercomputing 23.
23.
And I remember I saw it. I was like, ooh, I have to go show Ian. I have to get Ian to show him this.
Yeah, because it's like, yay, we finally see it.
Mm-hmm.
And I just happen to have a bunch of electronics with me. And there just happens to be the NVIDIA one right next to it. Funny enough. And I wonder if this will play. Yeah. There's a lot of power delivery on there.
Oh, yeah. Chonky VRMs.
So, yeah, cool. Show that off. So if you, yeah, so that's what MI300A looks like. We go back to this. So you've got two articles here. One on memory, and the second one is
the first one is actually looking at the CPU side of things.
Okay. CPU then GPU.
Yes.
Okay, so let's talk CPU.
So
I actually don't like this slide. It's not a good representation, but either way. Yeah, okay, so 24 core, 24 Zen 4 cores, 5.3 terabytes of HBM.
Yes, and yeah, so firstly, how do you connect all of this? So Infinity Fabric or Infinity Cache, and this is as far as I'm aware, the largest implementation of Infinity Fabric currently. It's huge. I believe it's 128 CMs, 30 CSs. It's an absolutely massive chip, and you do so to quote Chester from here, it's high bandwidth memory, not low latency memory. The latency out to memory for the Zen 4 cores is about 220 nanoseconds, which is about double to
consumer chip.
Just over double server, like a Genoa system. But in exchange for that, you have access to 256 megabytes of Infinity Cache, as well as a heap of bandwidth for what is only 24 cores, up to, I think, just over 300 gigabytes per second total.
Nice.
Between the three CCDs.
So what people are seeing here is, so the MI300 system is essentially, imagine 4 quadrants of compute. Each quadrant has 2 HBMs, and that's where you have the HBMs on the right hand side here. And in each of the quadrants, you either have 2 graphics dies, 2 compute dies, which are XCDs, or 3 CPU dies. So what it's saying here is the 3 CPU dies, the 24 cores, are directly connected to 2 HBMs on the same quadrant, or you have to jump to other quadrants to get to the other HBMs. But it all acts as one big chip anyway. So when George is saying this is the biggest Infinity Cache, what he's talking about here is, if you zoom in, you see it says CM and CS. These are all different elements of the Infinity Fabric that you have to put into your design to make everything connect together, because you need everything to talk together in a cache coherent way, and that's where the complexity comes in at scale. And then you also have to manage power and frequency and getting everything to work with all of these chips. It's difficult because you also need to bin them separately and everything else. But yeah, you can have the cores talk to the graphics. You can have the cores talk to the memory. You can have the graphics talk to the memory. You can have everything talk to each other. But doing it well is difficult. MI300A, everybody.
Yep. This is not easy.
Oh, this is a bigger, better zoom in one. Yeah. So And these CMs and CSs and ICs also all have caches to help with data movement.
Yeah, so I still don't fully understand how the Infinity Fabric. So basically the way that the Infinity Cache works is that it's all striped together, and it all behaves as one big system. Although you can't, there are certain hints that you can give it where it will try and keep things localized to a specific die versus trying to move it all around the chip.
Because all the cores are located in one quadrant, you do have an issue of data locality versus data non-locality. So you do have variable latency going to any other part of the chip.
Yes.
Whether it's next door or far away or on the same. So yeah, what George is saying here is that the chip acts like everything's equally spaced and equally distributed. It assumes latency is equivalent anywhere.
Yeah, so in theory it should be, because it is all striped together, but you can do, there are certain hints that the system can use to essentially say, hey, this is being used by this CCD or XCD, and it should really stay on this die. It shouldn't really be moved around.
This looks like a standard core cache.
Yeah, so the red line is client, that's client Zen 4. And then the blue line is MI300A.
So if your program needs 2 megabytes of data in its cache, it will sit here in the basically just peeking into the L3.
Yep.
And the latency of that data, if it's a consumer core, will be about 7 nanoseconds, but if it's this core, will be about 12.
Well, so these are actually these are the exact same core. The difference here is one of them is clocked a lot higher.
Yeah, that's what I mean.
Yeah, that the MI300A is clocked at 3.7 gigahertz, whereas the 7950 X3D non-Vcache die, so this is just a standard die, is clocking up to 5.7 gigahertz. So,
and the thing is, these cores have the same L1, L2, L3, but obviously beyond L3, on a consumer chip, you just have DRAM.
Yes.
Here you have Infinity Cache and then HBM.
Yep.
So when George was saying that there's a penalty for going out to Infinity Cache or DRAM, even compared to regular DRAM on a consumer chip, because there's all these little humps to go through, and that's partly due to the packaging design as well. So
yes,
yeah, but that's okay. It's a unique part with lots of memory bandwidth. If you can hide the latency, good. And this is you guys just showing off a hit versus a miss.
Yep.
Basically, and what that means. Yeah. Oh, and that's
so Gigabyte was generous enough to give us access to a full 4-node machine, and yeah, we were able to actually do some NUMA testing and what is the cross-node latency.
So
the cross-node latency here is in the 400 to 500 nanosecond range.
So the this is if you want one core on one chip accessing the L3 cache,
accessing the memory,
the HBM.
Yes.
On the one that it's an all-to-all connect. Is it an all-to-all or is it a square?
It is an all-to-all, but there is some notionally it should be all-to-all, but we do see some latency differences between. So it's 4. So let's say the one here is trying to access this.
Yeah.
This one, we see lower latency penalty for accessing this one versus accessing the one down here.
Is that a square root of 2 problem? Because it doesn't look like 2 hops. It looks like 1.4
no,
hops.
yeah, it may be a square root of 2 thing. I'm not positive. I don't know.
Yeah, it looks so inside the system. It looks like this.
Yeah.
So each CPU has access to 2 PCIe 5x16 slots, all-to-all connectivity, and then you also have a PCIe switch and some baseband management control. And
if I ever got one of these servers physically, you know what I would do? I would throw an OLAN GPU as my display out, and just run it as my daily. Is just an OLAN GPU just sitting there as a display out.
I have a feeling for day-to-day tasks, the latency might bite you. And also the power consumption.
It's for fun.
It's for fun. So yeah.
Hey, if I could afford to buy one, I could afford to pay for the power of it.
Yeah. So what's this graph showing?
That's remote access latency throughout the spectrum. So once you're leaving your caches, then you're trying to access the remote CCD
on a different chip.
On a different chip, yeah.
Okay.
So
okay, and this is the diagram showing it going through the Infinity cache.
Yep.
So the Infinity fabric, the IF here, accessing another chip. Okay. And then going to the full. I mean, guys, I'll actually what I should have done actually is copy this into the chat so people can follow along. I'll do that now.
So yeah. What's interesting is if you go down a little bit to this image.
You did a full quarter core on all 4 sockets.
Yes.
With hyper threading.
Yes.
For God's sake, George. Did this take a week and a half of the testing?
It took like I think it took overnight.
Yeah, this is 8 hours, easy. Yeah,
about 8 hours. And basically we finished for the night. We started up. We went to bed. We came back, and it was almost done. So we didn't waste time. Like it was basically done.
So for people who don't know, this is core-to-core latency, L3 XComp change instruction. Yeah. So
yeah, if you scroll down to the next sort of set of images, down, there we go, that one. So this one is the more conventional passing, just staying on a single node, passing. Yep. Passing between different chips, and the latency here is actually quite high. Likely the reason is because
packaging.
Yeah, it's just because this is not a latency focused system. This system's all about bandwidth. It's all about feeding
and power.
Realistically, it's feeding the XCDs, right?
The graphics tiles. Yeah. Yeah. So perhaps one thing that wasn't dictated right at the beginning. You have your 3 lots of 8 CPU cores, but there is an interposer connecting all of them. So it's like it's stacked. It's a interposer with some memory, and it has the memory controllers in it as well, if I remember correctly. But yeah, it's so you do have to go off a chip into an interposer, then back up to the chip. So that's why there's some additional latency here. You've also gone for yellow for 240 and red for 260, which is a 10% difference.
Yeah, it's just the way
stylistic choice.
Yeah,
I know.
Basically, emphasizing the differences. But yeah, sort of to end off. The actual performance of the cores, there's a bit more here. The performance of cores, basically the Zen 4 cores in MI300A gets you roughly the same performance as Zen 2, as a full-on 3950X at full bore, which for a product like this, it's pretty good.
You're talking about the
spec scores.
Yeah.
There you
so go. Testing a CPU, a standardized set of tests, spec CPU 2017 is very popular. It's well known. Because you have cores in this device that are low clocked, high bandwidth but low clocked, versus Zen 2, which is older but higher clocked, you're getting roughly the same. So Zen 2 performance with 224 graphics cores and 5.3 terabytes per second of memory bandwidth. I mean, Zen 2, that's console class. It literally is 3x a console on CPU.
And yeah, sort of the last bit before we get to the GPU side, since we are running at 2 hours 30 now, is the shared virtual memory. So if you scroll down past the cross node bandwidth stuff,
this one?
Down.
Oh, shared virtual memory.
Yep. So what this set of test showcases is, these are using the same pool of memory, and you're not having to go from a GPU to a CPU and back to a GPU, right? This is essentially showing zero memory copy, where you don't have to worry about moving lines between the GPUs and between a GPU and a CPU.
Sorry, just a second. I need to ban somebody on Twitch for spam. Yep. Sorry. Okay. Yeah, more details in the article over at Chips and Cheese. We've also got CPU to GPU nodes. Final words, core good.
Yep. Now, moving on to the GPU support, or the GPU side, excuse me. This is, you can see these are big old GPUs.
3/4 an MI300X. That's kind of what we're aiming for here.
Yeah, but what's interesting is the power target. So we actually were able to change the power targets between the 550 watt, which is designed for air or liquid, and the 760 watt power target is really meant for liquid cooling. But we were able to set the system to 760 watts. It was perfectly able to cool it
on air.
So we actually have data from both 550 watt and 760 watt.
Cool.
Yeah. What I find funny is, there's your throughputs. If you can see that the compute is reduced, though not by the 3/4 you would expect. It's actually
this is just one chip, not 4 chips.
This is a single chip. But MI300X does start running into some power limitations. Whereas at 760 watts, even though you do have fewer compute units, they can run faster. So you do make up some of that deficit. But yeah, if you scroll down, as you can see, actually go down one graph. This is an 8840 HS. So this is a standard client system. And as you can see, a lot of the operations per second, especially for FP64, is coming from the CPU side, right? A lot of the compute is from the CPU side. But if you scroll up back to the first one, It's all just GPU. It's oops, all GPU.
98% GPU.
Yeah. But yeah, scrolling down through, yeah, it's in many respects a smaller, it's a smaller MI300X, right? Now, if you get down to the benchmarks, the first benchmark here is
Or the atomic ads, or are you?
no, down FluidX 3D.
Okay.
Yep.
So FluidX 3D is a 3D rendering program built by Dr. Moritz Lehmann, who actually works for Intel now. But for a while, he was independent. And it's the sort of software you can use to look at fluid dynamics across Concord and multi-cell stuff.
And using FP32, what's really interesting is not only is there not much of a difference between 550 watts and 760 watts in this test, it's batching an MI300X. Like, it's doing pretty well.
Well, you've got fewer graphics cores for the same bandwidth.
Yes, and so that actually goes to show that a lot of workloads in HPC are memory bandwidth bound.
Yep.
So the loss of a quarter of your compute actually isn't that big of a loss.
And you get some benefits by having some CPUs on there, maybe.
Well, not just that, you also have power savings, right? If you can run it at 550 watts, and that's the whole system essentially. You don't have to deal with the CPU pulling power, the memory pulling power. It's all 550 watts right there. As you can see here, in a less memory bound test, the 760 watts does pull a little bit ahead, but it's not really there. Like
you got the Nvidia H100, and you got the Nvidia H100 here.
Yes. As far as like efficiency, the 550 watts is doing really well here. And the same story for the FP16C tests. Although the delta here is bigger. It is bigger, but still the efficiency run at 550 watts, be perfectly happy. Moving on to a test that Chester himself has made. This calculate gravitational potential is using FP64. And again, you can see that depending on the power usage, MI300A is bracketing MI300X. So again, we're seeing essentially a test that's memory bandwidth bound. And
well, the 210 is roughly a H100 as well.
210 does oddly well in this test, but
okay.
This was looking at the. What's interesting is even at 760 watts, it can't quite sustain 2.1 gigahertz in this test. Nearly, but not quite.
Again, it's air cooled, so
now. Unfortunately, I was
some of these are new tests that you've only been able to run on a couple of systems.
Is a simulating molecular dynamics, and this is a real benchmark.
GROMACS is in production.
Like production benchmark. Thank you. And I would have liked to have more numbers here of production software. Unfortunately, as I was trying to use the NVIDIA HPC Dockers, some of them I guess are kind of out of date and weren't working properly, and they weren't actually getting results. So I have a ton more. I actually have more data on MI300A, but unfortunately, because I wasn't able to get H100 data, it just couldn't be made into this article. But yeah, you can see Yeah, the 760 watts. Yeah, there's definitely a performance gain there, and there is, again, a significant difference between H100 and MI300A here. Unfortunately, due to time constraints, not just on the MI300A system, but also because it's expensive to run H100. We weren't able to profile these, so we weren't quite able to see why is MI300A doing well here, like so well. But I kind of suspect that, yeah, the zero memory copy may actually be doing some stuff here.
So Gunny asks, why does gravitational potential and fluid dynamics sound so much more relevant to me than large language model? Science!
Yeah. And
physics. That's why.
Yeah. There's one more set of test data that I have that I'll send you. If I could.
Is this going into an article?
No, this unfortunately because we couldn't. This was the very last minute set of data. So I'd already submitted the article to Gigabyte for final, like, so that they could say good. This is why I say it can do AI. Probably really shouldn't, like, it's not optimized for AI.
Yeah. Hold on, let me change Windows. And annoyingly, I need to, in order to change Windows, I need to stop sharing and then start sharing.
Yeah, so this is running. So this is Mixtral 8.7b, which is a mixture of experts model, with the input output length set to 128 tokens. And you can see that, yeah, if you want an AI processor from AMD, MI300X is your go-to. MI300A absolutely can still do LLM stuff, and it can still perform in large language models. But it really, as you can see, it really is more geared towards the HPC market. So
yeah, it'd be interesting if you had more time to have a full suite of Llama 3 3.1 tests. But
so
I know those take time, and
well, not just that. They're big models, so, and we had limited time.
Yeah.
So
you can only do so much in 2 weeks.
Yeah, I do wonder what Surf the Home did, because they actually had access to the exact same box. Actually, Patrick managed to get the exact same server that we were using to test, and actually physically was hands-on with it in Taiwan.
Yeah, let me share this one.
Yeah. Big ol' heat sink. Did a very good job with cooling it, I'll tell you that much.
Yeah, because you didn't actually, because the system was remote, you didn't actually get a hands-on with the system.
No, it was
in that one.
Across the Pacific. So
yeah, so this is the same picture from Supercomputing 23 that we saw in mine.
And then there's the working system.
Yeah, this is cool. Everybody should. I'll share this link because everybody should go give Patrick a view. And
if you don't already know Patrick from Surf the Home.
Yeah. So if they've got access to the system, they're going to have a review over the next few weeks.
Yep.
Yeah.
But yeah.
So now it's a case of having GoFundMe to get the 125K to buy one off eBay.
That would be cool. I would absolutely love to do it. But the likelihood of being able to spin up a GoFundMe for 135K to just be able to go buy server, not likely, unfortunately.
So you remember when we were talking about Nvidia, and they said that 15 of the top 20 games now use DLSS.
Yes.
And I said, how many people played a top 20 game for 2024 in 2024? The results are in 149 votes, and 59% of people said no.
Interesting.
So, so almost 2/3 of people don't play a top game of the year in the year. So, I mean, if you count Balatro, I guess I'm in the yes.
Yeah,
but it wasn't a AAA game, so
yeah,
I would have said no.
And also, Balatro is like, I played it for like 10 minutes. It was fine. Like 90 minutes. It's fine, but Slay the Spire or FTL personally for a roguelite.
Yes, Richard, I know it's 3/5, not 2/3. I was oversimplifying. But yeah. If anybody was wondering, the chip that's between us in this wider shot, that's the 5090. It's a special press bin edition. So we've got some small time for some Q&A. Because we spent so long on Nvidia, but I guess because they only launch a new card every 2 years now, it seems.
Yeah.
It was worth talking about.
I guess one last point, just real quick, like 60 seconds. ARM has formally refiled against Qualcomm. No jury verdict on question number 1, which was...
We'll cover this next week.
Okay, sure.
We're pushing it to next week.
Okay, fair enough.
Next week is also, for those of you who follow the financials, next week is financials week, or at least the start of. Let me... so on Wednesday, we have ASML, IBM, Meta, and Microsoft.
Wow.
On the Thursday, the 30th, we have Apple and Intel. On Friday, the 31st, we have Samsung Electronics. And then the week after, we have AMD, Google, ARM, and Qualcomm. So if you're into where people are making their money, and if you're wondering why nobody's making any money in gaming except Nvidia, it seems. And it's also because these are financial disclosures, they have to be truthful and honest, and sometimes news comes out. So we'll see if news comes out as well. I spent this morning updating my numbers for ASML because I realized I hadn't updated my graphs in a couple of quarters. So some of these companies I'll cover every quarter. Some of them I'll cover once a year or so just to get the feeling of where it's going. So we'll find that out. Some people did ask questions, and Dom, who exists in our backend, has curated some. So Davina asks, any possibility of using HBM instead of GDDR7 in the future? I think she means on consumer. I mean, we did have a few AMD chips with HBM.
But I don't think we'll ever see HBM in the consumer space again. I think realistically, HBM as it currently is, as far as I'm aware, doesn't really have low power states anymore. Like, a lot of that has been kind of stripped and to simplify stuff. So it doesn't idle like, I think the idling on the MI300A system was like 90, 100 watts. And so some jurisdictions just would not allow that.
One of the complaints with Xeon Max CPU, so that's the HBM add-in to Sapphire Rapids, which is HBM enabled CPU, whatever. And there was high demand for workstation use for that chip, but because it, as George said, because it didn't have low power states, it couldn't get Energy Star certification, and you need that to be able to sell. Because a workstation is considered, by and large, a prosumer product. If it's a business sale, I'm not sure how what the rule, if the rules are slightly different for
It's
that. So
different for a business or a server.
Server, yeah. But if it's a workstation, that's a class of machine that sits next to somebody,
Yeah.
rather than a dedicated power environment. So, Kiwi Sorbet asks, is data center Blackwell made on N3E? No. N4. Or N4P NX.
4NP to use. It's 4NP according to Nvidia, whatever that means.
Yeah. Yeah. So any more info? So Creeper 9000 asks, any more info on the on-chip memory dedicated to tensor cores on each SM? Because you said quarter of a megabyte per SM100. Any color on SM120? Or is it just disabled?
Well, so we know that there are PTX instructions for some of the tensor core operations on SM120. But what exactly it is, how much like memory there is for SM120 versus SM10, there's not enough, like there's not enough color there.
Yeah. Okay. So Richard Yao has just asked, is there any chance of seeing a 1024-bit bus with GDDR7 to let regular people get bandwidth close to HBM3E? Power.
No. Well, not just power. Where are you going to put it? Like
a 1024 shoreline.
Like, yeah, well, not just shoreline. Like the 5090 PCB is already an insane number of layers. If you wanted to do a clamshell, you would need even more PCB. No, like 512 is realistically your limit. You're not going much further than that.
Well, what is the highest bit bus on a GDDR?
512-bit. It was
consumer.
It was with Hawaii and now the 5090.
Okay. Cool. Does Google plan to release TPUs for external customers? You can buy them today. It's called the Coral TPU. If you
no,
if you go to Coral AI, and I'll share this screen. This is a collaboration with, in part with Google. You can buy a USB accelerator with the Edge TPU. Now, this is
a TPU device.
It's first gen TPU as well. First gen architecture. So yeah, no. Meow 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 says nope, not that, lol. Unfortunately, this is all you get.
Yeah.
So as I did share a picture of Google Axion on my Twitter feed like last week, 2 weeks ago. And they said, yeah, you can speak to our PM about that. And my first question got him so riled, he refused to answer any other question that I asked him.
What did you ask?
So I thought, let's take it from the super base level before I get into the architecture. Then, I'll work my way up through the stack, essentially. So I have a line of questioning that makes sense. Question 1. Do you partner with Broadcom for the physical design of your chip? Sorry, we're not talking about that. So I was like, well, the reason I'm asking is that I'm speaking to a lot of investors, and they're looking at, all the custom ASIC players, and especially the ARM CSS users with those, to find out how the market is shifting to custom ASICs and what are the value adds and the benefit. Oh, we're not talking about that. Okay, can we start talking about the architecture? No. Well, I know it's ARM Neoverse. Yeah, we're not confirming that. It's in your press release. So he got very ag just me mentioning Broadcom off the bat. Perhaps I should have started lighter. So yeah. Sal Miyake asks, are you disappointed that Nvidia has been steadily reducing the FO precision of their tensor cores? They are now FP4, and it's a shame that they can only be utilized by AI matrix multiply and for nothing else. Well, you can still use higher precision on them.
Yeah. I mean, like the data center stuff has FP64 capabilities still for the matrix operations.
For the tensor cores, yeah.
Yeah.
FP4 is a limit, not a sole unique class.
Yeah.
I mean,
actually,
there's only so much further you can go from FP4.
Yeah.
You run out of bits eventually.
I know
FP0
that
doesn't exist.
Intel's XMX units on Alchemist actually go down to int 2.
Yeah. Well, technically they do int 1.
Yeah.
FP1 is where it's at. All you have is a sign.
That's it.
Sign bit, positive or negative.
Yeah.
So, Elad has an interesting point that says, honestly, maybe the next thing is optical memory interconnects. I may have had many calls about this recently. Actually, it's part of the presentation I did. I did a presentation at the weekend for the Chinese American Semiconductor Professional Association. And it was recorded. It was a virtual thing, but I have a brand new slide deck. It follows some of my older slides that I've done before, but I also added new sections in it, which should be, I'll make it into a video when I get the chance, but it's not a priority. And in that, I do mention optical interconnects. And I had a call today with an investor about the state of optical interconnect and design and what needs to happen before it becomes productized. So, I just want to add this, Richard, on the AI 100 Ultra, that's 4 chips.
Mm-hmm. I responded and I linked him the GitHub. It's four AI 100 chips linked together in the AI 100 Ultra.
Yeah. And Gunny says FP1 is basically the binary equivalent of A.
Yeah.
Are you sure you want to do that? Sal Miyake asks, how come it says that Tensor Core's 5th gen are 32-bit in size and market that they're doing FP4 calculation? It's because you can do 8 FP4s.
Yep.
So that's YJ asks, why does your game need to be realistic though? Some people want the dogs of war. I mean, how realistic is Call of Duty these days anyway? Our good friend, some gadget guy, Juan Bagnell, I'm not sure if he's here, is that it's wild that the fidelity of AI faces is reaching a point where after it's sent to a compressed social media feed, it likely won't be detected as AI anymore. Social media image fidelity is garbage.
Not wrong.
So,
you don't want to know what I had to do to get that big old C2C latency chart to fit in the Substack.
Impulse 60 actually disagrees with your data center as a data storage medium concept by saying we can just start deleting data. Nobody said we had to keep it all. I
agree with Davina on this. They never will. Like Google, Microsoft, they all see data as currency.
Yeah. It's, so I had a conversation this week of explaining 5 years ago, 10 years ago, we were speaking about big data. Mm-hmm. And the data center opportunity was in analytics on big data. How can you make your data make you money if you even know where it is to begin with? Yeah, machine learning is just accelerating that to the point where it's not much of a conversation anymore, or at least we're talking about it in a very different dimension. Joseph Thomas asks, what kind of investors do you talk to? What are they invested in? So a bit about my, my day-to-day when it's not YouTube or it's not doing marketing consultancy is Wall Street investors, either individuals or funds or even buy-side analysts, for example, will turn around and say, hey, can I pay for an hour of your time? And I want to ask you a bunch of questions on 3D packaging or the AI industry and, or competitiveness, or where do you think optical interconnect is going over the next 2-3 years? What are you hearing from industry? These conversations, because they're all financial based, they all have to be only what's on the record. But the point is, these people don't want to spend 500 hours of their time doing research. So they pay me for an hour of my time to condense that down into a Q&A section. I do a couple of calls a quarter or so to Q&A groups. So this will just be like a one-headed Q&A, but they'll have like 10 to 30 clients on the call who are emailing in questions as I'm speaking about certain topics. So for example, the whole Stargate announcement that's being discussed in these calls. I used to do a lot of consumer CPU market, but obviously because AI is here and I spend a lot of time looking at AI startups and where their funding is going, that sucks a lot of energy out of the room. But yeah, it's people who have signed up to my Substack at the top tier also get an hour of time along with the subscription. I've had people use that hour to take me to dinner just to talk crap about the industry, or it's people who have been reading me for years and years and now know my YouTube channel and just want to hang out and chat. In some circumstances, it's like a parasocial relation engagement, right? Because people know who I am. In most of the circumstances, though, it is literally just institutional investors and funds who want to ask a domain matter expert, which apparently I am one, of his opinion on certain areas. But the thing is, they won't just ask me, they will ask 10 others, because then they get a range of opinions that affect how they look into their models. So it's like 8 out of 10 analysts expect PCIe switches to grow in the next 12 months because of product X, Y, and Z coming to the market and the opportunity that's enabling. So perhaps we have to go look at the PCIe switch companies and what their revenue models are doing, and is this something we want to invest in? Honestly, it's easy money, but I really enjoy it because on some level it's education. I'm teaching people about what I know. Now, they may be deep into semiconductors, and sometimes they're way more knowledgeable than I am, and I have to put up my hands up and say, I'm sorry, you clearly know more than I do. But a lot of the times it is people who are tasked to look at the semiconductor market, but they're not engineers. And it's really good fun. And I'm glad for the opportunity. And again, it pays quite well. It's a slow growth industry because right now I'm getting calls because it's financial season, right? But then after financial season, it will die down to nothing for 6 weeks again. But it's fun. I like it. And if you're interested, you know my email, or go to one of the expert networks. I'm on a couple of those. Or you can ask George about MI300A. He'll happily tell you about MI300A.
So much fun.
Quickscoper asks, will we get more specialized processor parts in the future? For example, Intel CPU has PE and LPE. Cores, no. Accelerators, yes. And we get new accelerators every generation, AV1, encode.
Yeah.
And then next generation we get decode first, and then encode. And now Blackwell has got 422 10-bit decode encode, and more decoders and more efficient decoders. The way chip design has grown over the last 20 years, aside from raw IPC, is dedicated acceleration. That's what NPU is. Now, are we going to get more specialized general purpose cores? These cores all target a specific performance, power, and have to work at a range.
So,
right? Question is how many you put on and what range that is.
What you could see is more specialized processors within a processor. And what do I mean? And what I mean by that is look at Intel AMX. It's essentially a separate accelerator within the CPU core itself.
Mm-hmm.
And so, yeah, you could see that. I could see that happening. But in terms of more generalized purpose accelerators,
yeah,
we're kind of running out of those.
Richard's got a bunch of questions here. Why are we not seeing AMD increase the layers of 3D V cache?
Simple. It's not cost effective to go more than one really right now.
Also, consumer workloads don't scale to more than one.
Yep.
Beyond more than one. So they haven't done it in enterprise yet either. The reason why there's not a Turin X, as in a Turin with Vcache, is because there's been no demand for it. The people who use those processors don't upgrade every generation. So they did 2 generations, now they're skipping 1. And if you don't need to include it in the design, you actually save some die size. So, Gunny asks, what happens to PhysX anyway? It became a software plugin because it turns out stuff is really, really fast now. So you don't need dedicated ASIC or FPGA to do it. PhysX is still used in a lot of games. Borderlands was the last game, or Borderlands 2, maybe even 3 or 4, is the last game I know where there was actually a toggle for it. But as it stands today, it's just natively on if you need it. It's just part of the library of DLLs and functions that become part of Unreal now. Richard asks, why did the industry reinvent the wheel with Ultra Ethernet instead of just using InfiniBand?
Because InfiniBand is not the be-all, end-all. You're
conflating 2 things here. InfiniBand is an NVIDIA-specific only technology. They do not license it externally.
Well,
so everybody... Hang on. Let me keep going.
It's more complicated than that.
But high level, super high level.
Yes.
The alternative is Ethernet, right? And Ethernet's actually the main player in all of the industry over InfiniBand. InfiniBand has some benefits over Ethernet, but Ethernet is ubiquitous. Ultra Ethernet Consortium is not a new thing. It's not a reinvention thing. It's an attempt by the industry to pull together to accelerate the standard in a way that everybody agrees with. This is especially important because we are going from 100 gig to 200 gig to 400 gig to 800 gig. And next time is 1.6 terabit. Now, a copper cable, they know it works at 100. They know it works at 200. It definitely works at 400. We've confirmed that. 800 is a push. They think they can get 1.6 to work, maybe.
And past that, no shot.
After that, it's all optical. You have to use optics. So rather than have the Ethernet standards body dawdle along with various contributors, they just turned around and said, let's be forthright about this and drag it by the horns into the 21st century because we need a competitor to InfiniBand. InfiniBand also has some amount of vendor lock-in. If you buy InfiniBand, the only way you can upgrade that system is with InfiniBand. Or you rip it all out and you use Ethernet. NVIDIA still has an Ethernet product, Spectrum. They cut some stuff out of the standards to make it go faster. That's their value add. But it's still Ethernet at the end of the day. It's still built on Ethernet. So, yeah. Let's so Disley asks, how does MI300A compare to Microsoft's special all CCD HBM EPIC chip?
No idea. Hasn't hit GA. When it hits GA, we'll look at it.
Yeah, that's the MI300C for people who are wondering. Isn't InfiniBand a mix of future I/O and next generation I/O? InfiniBand is able to be more agile, so they're adding things that other standards bodies haven't put in yet. So, I did see somebody say Intel 18A video when, still working on it. Sorry. And yeah, that's 3 hours and 10 minutes from the start of this stream. Let's go have dinner, because I also have some stuff to clean and emails to answer.
Lunch.
Yeah. Sounds good. This has been a fun stream. I can't believe we spoke about NVIDIA for an hour and a half. But hey, slides.
Yes.
Let's talk about the cool stuff. You know, to be honest, when I first started my channel, I thought what I'm going to do is I'm going to get slide decks like these and just speak through them, and that'll be all the videos on the channel. We still do that. To be honest, I think it's worked better with the two of us, because there's some things we don't understand, or the other person's understood, and ping-ponging ideas, we get it stuff. So all good. Thank you all for watching. We will be back again next week. We've got some topics to talk to you about, and all the financials, if you're interested. But again, thank you all for watching. I'm Ian of Tech Potato.
And I am George of Chips and Cheese.
And we'll catch you on the next one.
Have a good one, folks.